So in the Jewish tradition, there's a saying. Okay, the Talmud. Did any of you hear about the Talmud? The Talmud is a compendium of Jewish knowledge from about 2,000 years ago. The way the Jewish knowledge goes is there's what is called the written law, and that's the Torah, which is believed to have been given by God in Mount Sinai about 3,500 years ago. That's the written law. And the written law serves as an axiom, as a set of axioms. It's basically a law of the things that you should do in order to live a right life, like to help the needy, and there's a set of what we call 613 commandments. Some that you do and some that you don't. But those all serve as axioms. And then there are rules of inference where these laws are used to generate laws in cases where that didn't exist in those days. So for example, the laws of the Sabbath are what you cannot do in the day of the Sabbath in order to make it a day of rest. But what happens if these laws were given 3,500 years ago? There were no cell phones, televisions, all these things, electricity. What is allowed and what isn't allowed on the Sabbath? So there are rules of inference to infer from that about things as they change. So the Talmud is the compendium of the rules of inference that was written about 2,000 years ago. So that's already 1,500 years after the original, the written law. Until then, it was all oral. So the rules of inference were all passed orally, as well as the deductions, but they realized that it's growing, needs to be written down. So it was written down then, and since then there's a huge body of work on Jewish law in the last 2,000 years also. But 2,000 years ago, in the Talmud, there was also a place where they say, where it's called Ethics of the Fathers, about ethical behavior of people. And that one is more of advice of how to be an ethical person rather than rules that you can punish someone for not doing. So it's not laws in the sense of the things you must do or you must not do, but it's more how to be a better person, why it's called Ethics of the Fathers. And one of the things that it says there, and this whole introduction was for saying, there's one of the advices they give, Lo abaishan lamed, which means he who is shy cannot study well. If you want to learn, you can't be shy. You have to go up and try and give it. And it goes right after that, it also says, the next one is, Velo akapdan melamed. So lo, you realize already, is not. So not the shy. So that is, Velo akapdan melamed. Kapdan is someone who is very strict. So anyone who is too strict cannot be a good teacher. So it goes together. If you're too shy, you can't be a good student. If you're too strict, you can't be a good teacher. So as you can see, the ethics there go both ways. So I try not to be too strict. Here, of course, I can't be too strict. I can't even fail you. So, so I can't be too strict even if I want. But if anyone wants to come up and let's work through this, see how you were thinking about it, and where you can come both of you together if there's strength in numbers. Then there will be 2 against 1, and if not, then I'll start. Next time. All right. There will be a next time. Okay, so let's think together about this thing. We saw how we were supposed to build the automaton. We said, first of all, we put in the starting state and the ending state, and this is 0, 1 up to m. These are the state numbers. And here we put the first pattern symbol, the second pattern symbol, etc., up to the mth pattern symbol. And these are all the success links. I think the black worked better. Where did I put it? Here. We said, there was also one here, of course, not P1. And we said that as far as the failure links, so let's assume that we are here in I, and we already have all the failure, well, we have all the failure links throughout here. And now we're in I plus 1. Now we're in I plus 1, and we want to know where should the failure link go from I plus 1. So we said the following. Let's look at the failure link of I, and it went up to here. If the letter that's written up here, if this symbol, let's call it S, is equal to the symbol S here, then we said this would be the failure link of I plus 1. So that was the easy case. First of all, in fact, I waved my hands a bit here also. But this also needs a proof, a formal proof. It's just that at some point one assumes that the reader is capable of doing these formal proofs by himself or herself. And so therefore we don't do this, not to have everything too long. But so there's a joke about a professor who was teaching something once, and he said about something, okay, it's easy to see, and he moves on. And one of the students, as I said, lo baishan lamed, it means the shy student can't study. So he raises his hand and says, excuse me, you say it's easy to see, but I can't quite see it. Can you explain? So the professor says, well, of course. And then he goes, 1 second. He thinks a bit, and then he starts writing on the sides, and he writes and writes and writes. Says, okay, let's call a 10 minutes recess. And he goes to his office, and he's sitting there and writing and looking at all kinds of books and writing and writing. 20 minutes later, he comes into the class and says, like I said, it was trivial. And he goes on. So, so sometimes to say about something that it's easy, you have to be careful. And that's a joke, but there are true stories about things. Professor Furstenberg, who was my professor in homological algebra many, many years ago, was a huge mathematician. He was one of the best algebraists in the world. He said once in some class about something that it's trivial and moved on, and one of his students got a master's degree because he wrote a paper proving that this claim is even false. It's not only not trivial, but it's false, and that was the paper that he got his master's degree on. And then another student got a PhD proving that the statement is true under certain conditions, and under which conditions it's true. That was his PhD. So therefore, while we do need to sometimes say about things that, okay, it's clear and to move on, but it's always a good idea to make sure that it's really true when we say that it's clear and before we move on. So when we say, so the first thing that we said, that if there's a fail link that goes here, and this symbol is equal to that, then the fail link of I plus 1 goes here. Why would that be true? So there, in order to show that it's true, we need to prove two things. One, that okay, so let's say that I went to state J, okay? So the first thing we need to prove is that P1 through P J plus 1 is actually equal, so that prefix, we need to prove that this prefix is equal to P I minus, we'll say minus what, up to P I plus 1 I minus J, would it be? It's either I minus J or I minus J plus 1, but the point is, I'm never good about these things, which is why I'm not a computer and which is why I'm a theoretician. But the point is, we want here, okay, let's see, I plus 1 minus I minus j is equal to j plus 1. Okay, that's good. So this is the, so these are the correct numbers. I decided not to say it's easy and trivial. So the point is, this is the prefix up to j plus 1, and we want the prefix of length j plus 1 to be equal to the suffix of length j plus 1. So the first thing we need to do is to show that indeed this prefix is equal to this suffix. So when we have the back arrow pointing somewhere, it's pointing to a correct location. So we need to show that. The second thing we need to show is that it's the longest prefix that is equal to a suffix. So 1 that is written here means that the prefix is equal to the suffix. This means prefix equals suffix. The second thing we need to prove is that this is the longest prefix that's equal to the suffix. Okay, so these are two claims that we brushed aside yesterday, and we said, okay, this is obvious. And it is obvious, but it needs to be proven. Okay, so point number 1. Why is this prefix equal to a suffix? How do we know that? Maybe it's not. So what did we assume inductively? That's right. We assume that position I is correct. That's excellent. Now, assuming that it's correct, it means what? That the prefix 1, that P1 through Pj is equal to Pi minus j plus 1. No. I minus j to P of I. So that's the induction assumption. So that we assumed. Now, what else did we assume? That S is the letter that is written here and here, which means that Pj plus 1 equals S, and that's also equal to Pi plus 1. So Pj plus 1 is equal to Pi plus 1. So it means that if this is equal to that, now you add Pj plus 1 and Pi plus 1. Since they're equal, it must be equal. So we concatenated two equal strings and equal length strings. So the result has to be the same length. So indeed, the first thing we needed to prove is correct. Okay, now what is the second thing that we need to show? Is that this is the longest prefix that is equal to a suffix. Now again, let's go to the picture, because I don't know about you, but seeing indices in front of my eyes never aids to my understanding. After I understand something, I can always go back, like you saw here, and figure out the formula and put in the indices, and then you look very smart when you write the paper. You have all these indices running all over the place, and what the heck does he want? But to me, that always comes second. First comes the understanding, and then you can translate it. You can translate it into the formula. Now, the formula are necessary because really, when you write something down, it needs to be written down formally for posterity. So the formula are important. I'm not saying it's not. Don't go out there quoting and saying, Professor Amir says, no, forget about formula. No, it's necessary. But for the understanding, the first stage has to be the understanding of the principle. So let's see what's the principle here, or what happened here. So we have the pattern, and we stopped here. That was location I. So we have the pattern from 1 to I. And what we know is that this is the longest prefix that ends here in I. Now, what we said is that here we are now in I plus 1. And we want the longest prefix that is equal to the suffix here in I plus 1. So we said, and this is the location that we're talking about, since the symbol here is S and the symbol here is S, so what we claimed is that this is the longest suffix. Now here is where the other color is going to come in handy. Here to here is the longest suffix that's equal to the prefix up to I plus 1. So this is what we're saying now. What we proved is that indeed it's a prefix that's equal to a suffix. And we proved it with the indices and with the formula, but in the picture you can see right away that it has to be. Because if this is equal to this and this is equal to that, then clearly all this is equal to all that. So the picture shows it right away. But what we're saying is that it's the longest. Now, when we're saying it's the longest, we're trying to, so what we need to show is that it can't be that there is something else here that is longer that's equal to something here. And that is even longer than this. So that's what we're trying to say, that there isn't anything longer. If you look at the picture, you'll right away see that it can't be the case. Because were it the case that there was something like this, so obviously it has to end with an S, right? Because if this is equal, if this prefix is equal to this suffix, then it must, and we know that this letter is an S, so it must end with an S. But, okay, so now cut off the S and look at the red from the beginning till here, without the S. Because it was longer than the blue, it's longer than the blue. What does it mean? It means that the black that we said inductively was the longest prefix that's equal to the suffix up until location I was not really the longest prefix that's equal to the suffix, because this red gives us something longer. So that contradicts that assumption, therefore such a red cannot exist. Okay, so now I'm not, at this point, you will forgive me because I think that I'm not going to actually stand and write it on the board, but were I to write it, what I would say is assume that there was a longer one, and you would assume some index k that's longer than j plus 1. So assume that there is something of index k that's longer than j plus 1, suffix that's equal to a prefix. You prove that the last symbol of this substring of length k, meaning p of k is equal to s. And it's equal to s because that is a given. We are given that the last symbol is an s because we're given that that's the symbol p I plus 1. Now, if we get rid of that last symbol of the symbol k, what do we have left? We have left p1 to pk minus 1. But p1 through pk minus 1 is now a prefix that is also a suffix of the string up to location j. But k minus 1, but since k was longer than j plus 1, k minus 1 is greater than j. And because k minus 1 is greater than j, it means that we just found a prefix, p1 through pk minus 1, that is also a suffix ending at location j, that is longer than p1 through pj, but we assumed that p1 through pj was the longest, and hence the contradiction. So I didn't write it, but I said every single word that should be said in this proof. Okay? So is everyone now calm that at least that first step of of how we build the automaton, the fail links, is correct indeed. Okay. Now there was a next step that we said. Well, suppose that it's not equal to S. Okay, so all this was assuming that Pj plus 1 is equal to Pi plus 1. But what if Pj plus 1 is not equal to Pi plus 1? In that case, what did Knuth, Morris, and Pratt tell us to do? They say, okay, follow the fail link. Let's now erase all that, and so we can draw a nice, unconfusing picture. I'll start again. One. So this was the situation, and it is not true that Pj plus 1. So Pi plus 1 now is not equal to Pj plus 1. There was when I was an undergraduate student, there was a mathematician, a French mathematician called Dieudonné, and he was pretty famous, but at that time, he was already 80 years old, which would today make him 120 something. So I believe he's no longer with us. But at that time, what they used to say about him is that when he would give talks, he would say A, write B, think C, and it should have been D. So with indices, nearing his age, I'm beginning to understand where he was coming from. But okay, so Pj plus 1 is not equal to Pi plus 1. And what we said was that in this case, what do? We follow the link. Let's not go all the way to 2. 2 is very confusing. We follow the link to, let's say, L. And we ask if Pl plus 1 is equal to Pi plus 1. If it is, then our fail link from I plus 1 is going to go here. So if Pl plus 1 is equal to P of I plus 1, that's where our fail link is going to go. And we continue inductively. Now, the proof here, which I am not going to proceed in doing, because since it's an induction, it's going to be very similar to the proof that we have just done for the case of Pj plus 1 equal to Pi plus 1. It's clear, but let's go through it in our minds. It's clear that 1 to Pl plus 1 is since Pl plus 1 is equal to Pi plus 1, it's clear that 1 through Pl plus 1 is equal to everything ending in Pi plus 1. So it's equal to Pi minus L up to Pi plus 1. So that it's clear. That was the first thing that we needed to prove. And the proof is exactly the same proof, because by the inductive hypothesis, this is actually a prefix that is a suffix up to here, because all these, you go back and it's always a prefix that's equal to the suffix up to now. So therefore, it's a prefix that's equal to that suffix. And so if you add 1, it's a prefix that's equal to a suffix to location I plus 1. So the proof of number 1 is similar to the, not even similar, it's identical. Just replace L by J, or J in the other proof by L in the indices. So it's the same thing, because we had a prefix that's equal to a suffix. Now, why is it the longest? Again, because when you add the last letter. If you had something longer, you would have had something longer with this letter before, and you didn't have. So the same proof, and we go on by induction all the way to the beginning. Either until we find it, or if we don't, then there is no such prefix. Okay, so this is where we were when I asked for volunteers to come out and prove the time. Now, so now that we know that the algorithm works, so this was the correctness of the algorithm, and even the correctness, to calm you down, is not 100% proven, because that second part, at this point I said it's the same as the first. And it really is, believe me. But if you don't, you can go and do it for yourself. Now for the time. So again, we know that the way to prove it is not going to be a greedy kind of proof. You can't say, well, every location, for every back arrow, for every failed link, I spend constant amount of time, and therefore the whole thing is linear. Because we know that we don't. And that's exactly the counter example to this is going to be something like A, B, A, B, A, B, A, B, A, B. So if this is the pattern, so if all the links are going to basically go 2 back, this is how all the fail links are going to go, because whenever you fail, you go 2 to the back and you still get the AB. And therefore, the failure link here, the next one, in order to figure out where I was, I'm going to need to go back and back and back and back and back and back and compare. Suppose this was a C. So none of them is going to be right. I'm going to go back all the way. And it could be that my work was M divided by 2, which is O of M. So in fact, here is an example. Even a worse example would be AAAC, but in AAAC, you'd actually have O of M. But okay, so you have M, not O of M. But in any event, all of these periodic things where you need to go all the way to the beginning because something broke the period are going to give you O of M. So we can't prove it that way. And the only way that we can prove it is the same way that we proved the search, is by doing some amortized analysis. And to do an amortized analysis, you need a potential function. And the potential function, like I said, it was very easy to do it that time with a counter, a simple counter. And we can use a simple counter here also. And I assume that that is how you started, right? Okay, so what did you say? Let's do a counter. Every time when I build the automaton and I go through a success arrow, what do? I was increment by 1. And every time that you go back, you decrement by 1. It could work, and it could work. And you could prove it, but you'd need to do some massaging on that proof. An easier way of doing it is to, what do you care about the potential function? Is it your dollars that you're paying this guy who's shooting the arrows? No. So let's give him $2 for every success arrow rather than $1. So every success arrow, he gets $2, and for every fail arrow, he gets $1 deducted from his annual salary. Okay, so we have our counter, and it would work. The guy would be very happy. He's going to shoot his arrows and try to rake as much money as he can. So yeah. But now we need to somehow find out a bound on the back arrows, on the fail links. And how can we do that? So let's consider as we're building the automaton. And we have all of these guys already built, okay? And we also have our F with as many dollars as we have, and we're moving forward. Now, so if there was an F here, now we have F plus 1 in I plus 1. So No, f plus 2, sorry. So we have f plus 2. But now, when do we go on back arrows? As we construct the failure link for I plus 1, that's when we're going through back arrows. And remember, and this is why I said add 2, because remember that you always have to go back at least 1, because even in the best of cases where you go back 1 and this is equal to that, but you still went back 1. So you're not going to be gaining anything if you just add 1 for every success link, which is why I said add 2, and then even though you just lost 1 in order to figure out the back, you're still going to be okay. All right, so we added the 2. We go back 1, so now we have f plus 1. So we now have f plus, this is even worse. Okay. So we now have f plus 1. And if everything is okay, we keep going forward. And if not, then we have to go 1 more, and we're going to deduct 1. And then we're going to go 1 more, and we're going to deduct 1 again. And et cetera, et cetera. We're going to deduct a bunch of them. And then we end up somewhere. So what do we want to show? Basically what we want to show is that f ends up being non-negative. Because as long as f is non-negative, our pluses are going to be more than the minuses, or at least 2 times the pluses are more than, our pluses are more than 2 times the minuses, which is going to, at worst, make us spend time 3m, which is still big O of m. So that's why we didn't worry about paying $2 for every success arrow. So how about then if we try to prove, so we want to prove some sort of lemma like we proved before, that this f is bigger than some state. Well, what state do we want f to be bigger than at the end of this entire thing? How about the state that we end up in? So suppose that after all of this thing, we ended up in state C. We go back and back and back, and we are here in state C. So that's where we ended up. So we want f to be greater than or equal to C. So let's try claim that f is greater than or equal to C, where C is the state where I plus 1's fail link points to. By the way, as I am talking, where did I diverge so far from how far you got? I assume you said, okay, let's add 1 for the, and then what were you trying to prove?
The exact same thing with the text.
Yes, okay, but with the text, there was a problem, because in the text, we had a text and we had a pattern. Here we're stuck in the pattern. So, okay, so I guess this is the point. This is the point where where it diverges from that proof. So up until now, it was the same, but the point that we diverge is what is this C that we want f to be greater than or equal to? So we want it to be greater than or equal to some state, but what is the state that we're going to choose? And so what we decide to do here, now let me say why I think that we decide to do, because in some sense it seemed like a deus ex machina, what I just said. Okay, let's do f greater than or equal to C that it points to. Now why? Why would I say that? Am I still in the fog of sleeplessness? Why? So you need to have a reason for these kinds of things. But think about what you're trying to say. You're trying to say is that you can't go back more than you go forward. That's the idea of the amortization. So we say if we go back, then we pay for all the way back that we went by going forward. And so therefore, if we go back more, we pay for that with what forward we went from the last time. And so, which means that that we have to count this going back. And this is how we count this going back, is by going forward. And that's why I said, let's see where we end up going back. And we subtracted all of that from the going forward. So take the going forward, subtract all the going back, and see where you are. You have to be greater than that. So how am I going to be greater than that? By having f greater than where we ended up. So we subtract from f all the going back, and where we ended up, we're still greater than that because we subtracted what we went forward from that place. So that's the intuition. The intuition gets translated by proving a claim. And so that's the claim that we're proving. So f is greater than or equal to c, where c is the state where I plus 1's fail link points to. And now here, we need to prove that. And the proof of this is again by induction. So at this point, once you know that this is what you have to prove, you'll be able to do it probably. I can leave you off now to yourself, because at this point the proof is similar to the proof that we did before. But the proof would be also by induction. On the number of back arrows that you went. If you only had to go through a single back arrow in order to prove it, well, then f was greater than or equal to I. Okay, so base case. I'm running out of these things. Maybe I should throw the bad ones away. Put them here. Okay, so base case is one back arrow. And the base case is simple because in I plus 1, f was greater than or equal to c minus 1. Okay, because in I plus 1, we ended up in c. So in I, f was greater than or equal to c minus 1. Okay, so that pointed to c minus 1. So what we did to f got 2 added by our success failure, and then we subtracted 1 because we just went back. So what we have is f plus 1. Okay, so if f was greater than c minus 1, then f plus 1 is greater than or equal to c, and that's what we wanted to prove. So the base of the induction works, and here you see why we added 2. I thought that that's kind of where you got stuck, but here we see why we added 2 and not 1, because you always add 1 and go back 1. How are you ever going to increase? So you say, fine. I mean, in the best of cases here, you're going to go through m back arrows. So clearly, if you go through m forward and m back, you need to do something in order to show that you're bigger than that. So that's why we did the 2. So in the best case, we end up having m back arrows, but in the worst case, we could have 2m back arrows. So So that's what happens with the induction. So the induction, and now I'm also warning you, because since time is passing at an alarming rate, so I'm warning you that I'm not going to fill in all the details on this proof, but I'm going to get close enough to the end, so that at this point really there is no leaps of faith that you need to take, only leaps of technical writing. So that I am less concerned with. So the inductive case, yeah, the blues write better, I know. So in the inductive case, we go through J back arrows. So the inductive case is we go through J back arrows. And so what's the idea? We go through J back arrows. We assume that going through J back arrows was good. We still have, if we, having gone through J back arrows, we still have F greater than or equal to that. And now, okay, so assume that going through J back arrows still gives F greater than or equal to C. And we have to show what happens when we go through J plus 1 arrows. Okay, so what basically happened? We went through all of these. We went down. And going through all of these means that we subtracted J from the F plus 2 that we started with. So we had F plus 2 that we started with, and we subtracted J from there. Now, in fact, I don't know if you even need the induction, but you go through J of them. Now, you end up in C. Now, what do we know? We know that that F was greater than or equal to the original C. If you subtract J of them, it means you subtracted J from the F, but meanwhile, you also subtracted J from the C. So every arrow that you go back, you also subtract from the C. Since the original F was greater than or equal to C from position I, you went to C and F was greater than that. Now you went through J arrows. It means that it's greater than C minus J. But that would assume that every arrow went back 1. You went back even more than 1, so for sure it's greater than or equal to C minus J. So wherever it is that you end up, your F is still greater than or equal to where you ended up. So that, again, is the wording of the proof, but the proof is there. So what you need to show is that as you go down and you subtract from your counter, but you also subtract from your state. And therefore, you're still greater than or equal to the state that you ended in. And at that point, the proof is exactly the same as the proof was in the search phase, because what it means is that throughout the run, we never had the counter negative, which means that that 2 times the failed links is less than or equal to the number of success links, that the failed links is less than or equal to 2 times the number of success links, which means that altogether you did not spend more than 3m time constructing the automaton. So this was the proof at the end. And so basically, you notice that where you didn't manage to make the next step was actually in a place, and you should feel good about that, was actually in a place where the next step was not just technically different, but there was something different here in the understanding, because we only had the pattern to look at, whereas Yesterday we also had the text to look at. So we compared ourselves from the text to the pattern. Here we just had the pattern. But the idea should be the same idea, and that would be that as I go back, what I lose when I go back is what I paid for when I went forward. And that is why you add when you go forward, you subtract when you go back. And that's why, since here I'm just counting the number of times I'm running back in the pattern, I have to find out where I am when I finished running back. And that's what gave us this lemma. Okay, so that more or less concluded yesterday's tutorial. And we can go on to new stuff now. Any questions? I warn you that I still didn't fill it down to the last detail, but I give you credit. You're smart people, and I'm sure that you can do that. But at this point, you have this information is now not anything. So just one last story about when you say about things that they're trivial. So when I did my my master's thesis, I actually published 3 papers out of my master's thesis, but my advisor was an old school. I really respect him to this day, but he was an old school guy. So I also had to write a thesis in addition to the papers that were published. So I wrote the thesis. It had to do with subrecursive hierarchies. So I wrote the thesis, and the thesis was actually even written in Hebrew, although the papers were in English. So I wrote the thesis and I submitted to him, and that was 10 days before I was supposed to go to, about a week, 10 days before I was supposed to go to the army. So, but I said, I mean, so what? I mean, I know that this was already published. There's not a problem. So I give it to him, and 4 days later, he really sat and read everything. 4 days later, he said, well, this is good except for one thing. Everything here is new. This is all the stuff that you have proven. I said, so what? He says, well, new is for PhD. In a master's thesis, you have to show that you also learned something. I said, but how could I learn something if how can it be that I didn't learn anything if I can prove new things? He says, no, I know what you're talking about. And I know that you learned something, but it has to be reflected in the thesis. I told you, it was old school, it has to be reflected in the thesis. So he said, and I started getting, not so much that I cared, but I only had a few more days, 5 days left until I have to go to the army, and I didn't know what he wants me to do. So he says, you know what? Here's the thing. You make heavy use of Gregorczyk's theorem. Gregorczyk's theorem has to do with primitive recursive hierarchies. You make heavy use of Gregorczyk's theorem. Bring the proof of Gregorczyk's theorem. Just have a chapter, the proof of Gregorczyk's theorem, and everything is fine. And I tried to convince him not to, for 2 reasons. First of all, Gregorczyk's proof was a huge paper. It was about 40 pages. Secondly, I didn't read Gregorczyk's proof. I trusted him. So yeah, I used his theorem, but I didn't read the theorem. So I said to him, no. He said, come on. This is child's game. I mean, you know the theorem. Go, just add that chapter. So I go, what can I do? He's the advisor. So I went home, and I started reading Gregorczyk's paper for the first time. It was an obtuse paper written by a Polish mathematician in 1957, translated into English. And the more I read, the more I get bogged down in the details and the indices, and the more I get frustrated and nervous and scared that I'm not going to be able to finish this in time. And so the whole night passes, and the morning, the sun is coming up, and the birds are chirping, and I have no clue what Gregorczyk wants from my life. So at this point, I was a wreck. I said, what can I do? I'm going to go to sleep now. I can't do anything else. So I went to sleep, got up somewhere in the early afternoon, and then I said to myself, listen, it's not going to work. You're not going to understand Gregorczyk's proof. But you know this stuff. You really know subrecursive hierarchies. So prove the damn theorem. So I sat down the next night, and I proved Gregorczyk's theorem. It was touch and go. It was a long proof. I did it a little bit, I think, more elegantly because it was only 30 pages at the end. But I proved Gregorczyk's theorem. I added it into the thesis, and I gave it to my advisor. Now, notice that I still didn't prove that I learned anything, but he didn't know that. So I gave him the thesis, and he right away authorized it. And okay, a year later, I was in the United States, and in those days there was no email, and letters would take about 2 weeks back and forth from Israel to the United States. But I get a letter from him, and in the letter, he starts by saying he hopes I'm okay, but then he says, you know, this is the most irresponsible thing that I've ever seen in my life. Who does this? How could you do that? I said, what does he want from me? So then comes the explanation. He said, well, I decided to give a graduate seminar about sub-recursive hierarchies. And so obviously you can't do it without Gregorczyk's proof. And I said to myself, I even have it written in Hebrew, so I don't need to go and read it from Gregorczyk's material. So I went from your thesis. And in the bottom of page 20, where you say it's easy to see, what do you mean it's easy to see? It took me a day in the library to see why this is true. This is such an irresponsible thing. How can you say it's easy to see? Now, I was happy for two things. First, that he didn't find any mistake in the proof, because I never really reread it. I wrote it that night. I typed it. I gave it to him. And to my defense, I would say that it probably was easy for me to see, because all those sub-recursive stuff was really, it was in my blood. And so it probably was easy for me to see, even though it wasn't easy for him to see. But when I finished reading the paper, you should have seen the smile on my face. You cost me 2 nights of my life. Spend a day in the library. All right. So, hilarity, but what do we know? So we know that when you're given a string, that when you're given a string, and you're given of length n, and you're given a pattern of length m, Knuth, Morris, and Pratt tell us that we can, no matter what the alphabet size, that we can find the text in the pattern in the text in linear time, in time big O of n. So in time O of m, we construct the automaton. Then we go through, and again in time O of n amortized, we can find it in the text. But now comes, we go to the next step. And the next step is, what happens? Yeah, that's good. What happens if what we want is to find something in 2 dimensions, not in 1 dimension? So suppose you have an aerial photograph. Here you have an aerial photograph of some city. And you want to find out whether in this aerial photograph, where is this? Where is this building? Because that's the building that you want to go to or do something. So where is it in this city? Well, you're not really going to find it, because this picture does not appear anywhere there. But if you rotated it, scaled it, at that point, it's there. So as it is, exactly in the form that you're looking for it doesn't really exist. But with rotation and scaling, you can find it. Now, in general, there are more issues that you need to concern yourself with. First of all, there are what is called local errors. Local errors mean, suppose that what you're looking for, that image that you're looking for, actually does exist. It doesn't need to be rotated and scaled or anything like that. It exists. But it does not exist exactly as it is, because it could be that it's partly occluded. So suppose you're looking for someone stole a Rolls Royce, and you're looking in the aerial photograph to see where that Rolls Royce is. Well, it's parked under a tree, and you only see the front of the Rolls Royce. You don't see the back. So parts of it can be occluded. So even if what you're looking for appears in exactly the same size and in exactly the same orientation, but it's still not entirely there, that would be a local error. That's occlusion. Then it could be that we have transmission and resolution errors. In other words, it could be that while transmitting the picture from place to place, or blowing it up, or there were resolution differences. So at the end, everything I have is right. But it has, like, on the transmission, some zeros turned into ones and some ones to zeros. So some things are not exactly the same. Everything else is. So that would be also local. Then there could be some details that are missing. So all of these would mean what I'm looking for exists, and it exists in the same orientation and the same size, but there are local errors. So that would be a little bit easier to find, but still you'd need to worry about it. Then, of course, there's the scaling, because maybe what you're looking for isn't there in the size that you're looking for. And then there's the rotation, because maybe what you're looking for has been rotated. And then, of course, you have to integrate all these issues in order to get an algorithm that solves a general thing. So the general would be, if I'm looking, let's say, for a nuclear reactor in Iran or something. So I take some pictures of how nuclear reactors look, and then I do all the aerial photographs or satellite photos or something, and I need to find anything that looks like these with differences of resolution and scaling and rotation, anything that looks like it. So that would be the final goal of all of this. Now, what I like to tell a lot of my friends is that the difference between theoretical computer science and, let's say, AI is that in theoretical computer science, when you have a hard problem, usually what you do is you simplify, simplify, simplify up until the simplest form that you know how to solve, and then you start adding the complexity. In AI, I have a great friend in AI, and I really love him. But whenever we think of a problem, and I tell him, this seems like a hard problem, he says, yeah, let's generalize. So there's a difference in how you view the world. But in our case, we simplify when there's something hard. So we would want to start from the very beginning, which means with local errors. But in our case, the beginning is even before that. In our case, the beginning is, let's do exact matching, but 2-dimension. So we know how to do it in 1 dimension. I want it in 2 dimension. So what do we want to do? Okay, yes. So the whole task seems daunting, right? I have to agree. And as a theoretician, of course, what we do is we start from the beginning, and as Alice said to the mouse in Alice in Wonderland, you start in the beginning, go on to the end, then end. So we start in the beginning. However, it does seem like a tough task, but there is hope. Why? Because of the following thing. I don't know how the birds are here, but in Israel, these birds are unbelievable. Every time that I wash my car and I wax it and everything is shiny, as soon as I go out to the road, as soon as I go out, and it especially happens when it's all shiny and I'm so proud of myself, there's a bird that discovers that car from on top and smack, right on the roof. So this is what happens. And so if this problem of detecting when my car is nice and shiny from the air can be solved by a bird brain, then there's hope that we should also solve it. So in fact, so I drew this for a conference that I spoke at in Morelia in Mexico a number of years ago. And everyone, of course, laughed when they saw it the way that you snickered here. And then this is the picture of the conference in Morelia. So in conferences, they always like to one day give you a breath of fresh air, so you don't sit cooped up in the room for 3 days from morning till night hearing computer science. It can drive anybody nuts. So one day they take you out for a trip. So they took us out for an outing, and here you see the local guide explaining to us the wonders of what it is to see. And these are some of the people from the conference. And as you see, this is me. And as we're talking, a bird did its thing right on my shoulder. And everybody turned to me and said, wow, so it's true. All right. So this is a little something, reminiscences from Morelia. But so as we said, string matching was motivated by text editing. And so this is what we saw, that if you have a text T0 through Tn and a pattern P0 through Pm over some alphabet sigma, K and P showed us how to find it in linear time. But let's generalize this, and generalize this to 2 dimensions, but in an easy way. So we have the text n by n, and the pattern is m by m, and all I want is to find all the places where this m by m pattern appears in this m by m text. So that's all I want to find out. I want to find exact matching. Now, this is also something I always tell my students, and when I was in industry, I always also told my programmers, whenever you're given a problem, the first thing you do is not think about what's the most complex way I can solve it, but think about the naive algorithm, the easiest one, because if that works, that's the best. If you see that the naive algorithm is too inefficient, then start thinking. But first try the naive algorithm. So the naive algorithm here, and again, so I'm giving you a pointer for the class, another assignment that could be for the programming class. So program it. It's a 2-dimensional array. So you're looking for a small 2-dimensional array and a large 2-dimensional array. And here you have 2 nested loops here in order to solve it. So what are they going to do in the programming class? They're going to say, okay, let's start here and let's compare this m by m square. And by the way, I did n by n and m by m. Obviously, it could be any square, n1, n2, m1, m2, but I told you already my abhorrence of indices. So the less indices, the better, and the concept can be understood clearly just by n and m. So we have so you look for the m by m pattern in location 1. So the time you worked is m squared for one location. Then you go to the second location, and again you work O of m squared time, and then the third location. So altogether, your time is going to be O of n squared m squared. So that's what the naive algorithm is going to do. Now notice that n squared m squared is not quadratic. It's not, the n squared is really the size of the input. So if our time would have been O of n squared, that's linear, because that's the size of the input. We always measure time as the size of input. So I just thought it would be more confusing if I wrote that the text is square root of n by square root of n and the pattern is square root of n by square root of n. So let's not get confused there. Before I go on, let me ask you, okay, so obviously still we don't want O of n squared times m squared. What we would want is O of n squared. That's what that's where we want to get. But can we now at this point, from what we know, as a black box, can we do it in O of n squared, faster than n squared m squared? So this is a question. This is not a rhetorical question. Take a couple of minutes, or even less than a minute, and think, what do you know how to do so far, and can that help you in getting a better time than O of n squared m squared? And if anyone has any idea, remember, lo abaishan lamed, so it means not the shy one studies, so tell me the idea. And if the idea is bad, remember, lo akapdan melamed, not the strict one can be a teacher, so I'm not going to stand here and say, this is the stupidest idea I ever heard in my life. What are you even doing here? Why don't you just go out? So I'm not going to do that either. And therefore, if anyone has an idea, I would like to hear it. Yes? Okay, so what you're saying is take the first row of the pattern. Use K and P. Okay. Excellent idea. So here's, okay. So now I can start learning names. So your name is? Everybody who says something, I'm going to try to learn his name. Uh, write it down for me. I told you, but you have to be polite, even though I have this foreign ears that. Vaidyanathan. Okay. Okay. Now, Nathan, I don't know what it means in your language, but Nathan in Hebrew means gave. So Jonathan, which is a name you may have heard, means Jah. It comes from Hebrew. It comes from Yehonatan. So Yeho is the name of God. It's like God gave. So it's like God's gift. Jonathan means in Hebrew God's gift. So what does Nathan mean? And does it mean anything or doesn't mean anything? So if Vaidya meant something in Hebrew, I would make you I would give your name a Hebrew meaning, but it doesn't. So I'm stuck here. All right. So we'll go on. You have to forgive me, but I have many interests, and computer science is just a hobby, and so a lot of things move me. So Vaidyanathan says the following. Let's take the first. So here's the pattern. We have m rows, and let's say that the rows are P1 through Pm. Now, P1 as a row is a string. So now let's take the text, and the text is an n by n pattern, but there's no reason why we can't write all these n rows one after another. So at this point we have an n squared length text, and we have an m length pattern. So in time O of n squared in time O of n squared, we can find all the places where the pattern starts in this big text. And in fact, the locations that are like in the border we can cut. If there's no if it starts here, let's say, and ends here, so obviously we're not interested in that. So we'll throw these away, but that's still in linear time. So if in O of n squared times, we can find all the places where P1 starts. And let's write it down. P1, 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 P1. And all we worked is O of n squared time, linear time. But now, let's look for the second row. So the second row is P2, and we do the same thing. So again, we work O of n squared time, and we write the second row. P2, 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 P2. We have all the places where P2 starts. And then we do the same thing for the third row and the fourth row. And at the end, we have all these P1 through PMs all over the text, written all over the text. And how much time did we spend in getting all of that? There were m rows. Each one was O of n squared. So in time O of n squared m, we now have a text with all kinds of P1s and P2s and P3s and P4s thrown all over the place. But what we want is to find the two-dimensional pattern. So we're not done. So give us the last step. Exactly. 2 points. So what we do is, that's like in a TV game, so he gets the 2 points. So he says, where does the pattern exist? The pattern exists where all the m rows are one after the other. But this is also like here. If we have P1 and underneath P2 and up to PM, if we have all of that, then that means that we have the first row and the second row and the third row. And if we have all the m rows, we have the pattern. So how much time does it take us to find this? That's also linear time, because this is now, it's a classic KMP. So it's O of n squared m plus O of n squared, which altogether is O of n squared time, n squared m time. Okay, so we saw that without too much work, just by using KMP as a black box, we find all the locations of the pattern in the text, and we do it faster than we would have done it not knowing KMP. So already we see that what we learned yesterday helps us today. That's always good. Yeah. Yes, it is O of n squared time. Okay. It's an excellent question. So what's your name? Manoch? Manoch. How do I remember that in Hebrew? So Manoch is asking the following question. He's saying, how do I know that I don't have more than one symbol in one cell? How do I know that it's P1 through Pm? Now, what does it mean that I have more than one symbol in the same cell? It means that there are some rows that are the same, that repeat. Because if all the rows are different, that can't happen. But it could be when the rows repeat. So if there's a certain row that appears more than once, then it could repeat. Then I could have two of these things in the same place. However, so the question is an excellent question, and I was going to talk about it in a minute or two, but it's a good thing. It's a good thing that the question was asked. So let's do a small pre-processing. Let's go through the pattern and find out which rows repeat themselves, and then we're going to give them the same name. So if row 1, so this is P1, and this is P2, and let's say that P3 is equal to P1, so I'm going to write P1. I'm not going to write P3. And let's say that P4 is equal to P2, then I'm going to write P2. And then let's say that P5 is not equal to any of them. So my pattern is going to be P1, P2, P1, P2, P5. I'm not going to have two cells having the same element, because that's what I'm looking for. And I'm not going to look for P1 through Pm, but I'm going to look for P1, P2, P1, P2, P5. But, you know, Mr. Knuth, Mr. Morris, and Mr. Pratt know how to do it for any pattern. So it doesn't need to be. Okay? So excellent question. And I urge all of you to not let me take any shortcuts. Make sure you always understand. Excellent question. That solves it. So now the only question that remains is, how do we find out quickly, because we need to do this quickly, how do we find out which rows repeat? So an easy way of doing it, there are many ways of doing it, but an easy way of doing it, and I'm going to take this opportunity and show it to you just in case you've never seen it before, and because I'm going to use this data structure in the future, and because yesterday I told you that we're going to do data structures and not just algorithms. So there's a beautiful data structure that allows us to do that in linear time. Linear time, the size of the pattern is O of m, is m squared. So in time O of m squared, we're going to be able to do this. And that data structure is called the trie. So everybody heard about the trie? If anyone didn't, raise your hand. Okay, so there's a few people who didn't. And so, fortunately enough, let's end this show. And fortunately enough, I have another show here that talks about tries. So what do we know about the trie? So the trie, for those who didn't know, a treat is coming up. It's a very simple data structure. And it allows us to do dictionary search. The way that you search in a dictionary in general is a kind of a binary search, right? Because if you're looking for a word in a dictionary, then you're going to look for the first letter, and you do a binary search for the first letter, then you do a binary search for the second letter, and a binary search for the third, and that is why we do this thing a lot faster than by reading the entire dictionary and looking for the word. So that's one of the things that we do in dictionaries. But binary search is only one way of doing it. When you're searching for a word in a list of words, and basically this is what we're doing here, because each one of these strings, you can look for it, you can consider it as a word. So I'm looking, I have a list of words, and I'm looking for a particular word in the set of words. So obviously it's true that in order to find out if the first row repeats, I could go through all the other m rows and do a binary search on every symbol and find out if it's equal, but I don't want to do that. So what I'm going to do is something even nicer, is use this trie. Now, a trie is really a labeled tree, but it's a special type of labeled tree. So we have a tree, and the vertices are labeled. So we have a tree, we have the vertices, the edges, and there's a label on the vertices, where every vertex has a label from some alphabet sigma. So sigma is our alphabet. Here's an example of a labeled tree. Our alphabet is ABC, and we have, in every vertex, we have a label. So that's a labeled tree. A trie is going to be a labeled tree, but a labeled tree with a certain property, and we're going to see what the property is. So we need a couple of more definitions. What's a path string? So a path, V0, Vi, in a vertex labeled tree. So any path that you have in a tree, and we're looking at this tree as a directed tree, so it's directed from parent down. So any path that you have, if you consider the labels on the vertices of the path as we go through, that gives us a path string. So here's an example. This is a path. We go from this vertex to this vertex to this vertex, and the path and the string that this path defines is AAB, because we just take the symbols that are on the vertices that the path is going on. Now, a root path is going to be a special kind of path in a vertex labeled tree, is a path that starts at the root. So the path that we saw before, this one is a root path, but this one, although it's a path and it defines a string, but it's not a root path. Okay. Now, this is a formal definition of the longest common prefix of two strings. So if S and T are strings, S is the string S1 through Sm, and T is T1 through Tn, and they're over alphabet sigma. The longest common prefix of S and T is the string A1 through AK, such that that string appears in both of them, but K plus 1 is already different. So again, it's what you would expect, and if you look for the longest common prefix of these two strings, it's obviously this, because they're equal. These two strings are equal all the way to here, but then B is not equal to C. So the longest common prefix is ABC, AAB, CDA. So far all these are definitions, and none of these definitions is really very hard. So we're going to define a trie T of n strings. So now we're finally getting to the definition of what a trie is. Now, the word trie comes from retrieval, because it was invented in information retrieval, because you want to find a word in a set of words. So they used the middle of the word. Now, some of you are going to jump right and say to me, wait a minute, so why do you call it trie? We don't say retrieval, we say retrieval. But the answer is that if we called it tree and not trie, then people wouldn't be able to hear the difference the same way that I have a problem with Indian names, but not with Brazilian names. But people would have a difficulty differentiating between a tree, T-R-I-E, and a tree, T-R-E-E. So they say, okay, so let's say try. So don't start saying retrieval, because people will then think you're from Australia. So still say retrieval, but this data structure is called trie, and that's the historical reason why it's called a trie. So now we're going to define a trie of n strings. So we have these n strings, S1 through Sn, and each one of them I actually broke down into its symbols that it's derived of, and they're all over alphabet sigma. We're going to define it by induction on n, on the number of strings. So I will show you what's a trie of one string, and then if assuming we know what's a trie of n strings, what would be a trie of n plus 1 strings. And it's going to be defined as follows. So first of all, we're going to have two special symbols that are not in the alphabet. And that's lambda, which is going to represent the empty string, and dollar, which is going to represent an end of string, an end of string symbol. So every string is going to end by a dollar, so we know that that's where the string ends. And the reason the dollar comes is only to differentiate between two strings, one of whom is a prefix of another. So in order to differentiate between them, if they all end by a dollar, then no two strings are going to be prefixes of each other, since the dollar only appears once and it's at the end. Okay, so how does the trie look for a single string? We have a tree that is really just one path from the root to the edge. The edge is going to be a dollar. The root is going to be the empty node, lambda. And every node in between, the label that it's going to have is the label, is the symbol in the string that we have. So we only have one string, and we want to build the trie for this one string. This is going to be it, the simplest way that you can do. Now, the inductive hypothesis. Assume that we have defined the trie Tn of n strings. Now we want to know what is the trie Tn plus 1 of n plus 1 strings. So these are my n plus 1 strings, and I already have the trie, or I know how to build the trie of the first n of them. Now I just need to stick the n plus first string into this trie. So the way we do it is the following. So Tn, as we say, is the trie of the n strings S1 through Sn. And now let A1 through AK be the longest LCP of n plus 1 and Si. LCP is the longest common prefix, right? That's how we defined it. So look at the longest common prefix of Sn plus 1 and S1. Look at the longest common prefix of Sn plus 1 and S2, and so on. Look at the longest common prefix of Sn plus 1 with all the n previous strings. Find the longest of them, and the longest of these is going to be A1 through AK. Now, A1 through AK is going to be a root path in the trie. So you're going to follow the root path A1 through AK, and then you concatenate Sn plus 1, K plus 1 to the end. You concatenate this path, or not concatenate, you add this path as a son of the path A1 through AK, and that would be the trie for n plus 1. Now, this is a very confusing definition, and anyone who hasn't seen a trie is going to say, what? And scratch his head, when it's really very simple. So let's see an example, because the example is unbelievably easy. So suppose these are our strings, and we want to construct the trie for that. Why is that? Because I think that how does it go back one? Okay, that's good. We have the empty strings, then we have A, B, C, A, B, B, C, dollar. Okay, so this is the first string. Now, the second string, what did we say? Let's look for the longest common prefix of this string and all those in the trie. Now, we only have one in the trie, and this is the longest common prefix. So the longest common prefix is AB, and then we still have B dollar, and we add it like this. Now, when I say longest common prefix, in fact, you do something even easier, because go down, take this string and just go down the tree as long as you can. So you see an A, you go down. You see a B, you go down. Then you don't see a B anymore, so add the path. Okay, now comes the next one. ABBA has nothing to do with the music group. So ABBA, now, if we're talking about the official way that it was defined, so you're going to say ABB is the longest common prefix. So in fact, you would say, okay, ABB, and then you add stuff. But the way that your algorithm is going to construct it, as I said, is a lot simpler. Okay, we have ABBA, so let's go down. A, B, B, and we don't have an A. So we add A dollar. And now we have the next row, ABCB. So A, B, C, and there's no B. So we add B dollar. Now we have BBAB. Oops, we don't even have a B. So we add B, B, A, B dollar. And now we have BABC. Okay, so we have B, but we don't have A. So we have A, B, C, dollar. So this is a trie. Now you saw how easy it is to build it, and it's totally linear time buildup because you take these strings and you put them in one by one. You go in until you can't, and then you continue going. So total linear time to build it up. However, one second. However, the beautiful thing is retrieval here is also linear time. Because suppose I ask you, is the word ABBC one of the words in my group? Well, all you need to do is time O of the length of the word ABBC that you look for, because you're going to say ABB. No, I don't have ABBC. So you say, no, I don't have that word. Is the word BBAB in? So you say, let's see. BBAB, yep, it's there. So the beauty of the trie is that it allows you to do like a search in a dictionary, but the search is not the length of the word you're searching times log of the dictionary for the binary search, but just the length of the word you're searching. Especially if your alphabet is constant. If your alphabet is infinite, you're still going to have some log. But otherwise, you don't lose anything. It's like a total constant time algorithm. Now, in our case, where we have this pattern, and we want to find the pattern, so build the trie of the pattern. It's O of m squared. But every time that you come with a row, and you see that it's there already, then give it the number that is there. So in linear time, O of m squared, you can construct the number of rows. You can construct the pattern of the rows, and then you look for it in time O of n squared m, and then in time O of n squared, you find you use K and P to find the whole thing, and you're done. Let me see if there's anything else here that I said about tries. Probably not anything serious. Yeah, so the construction time, as I said, it's total linear time. The insertion and lookup and deletion time is O of m if the alphabet is fixed, and if it's unbounded, it's O of m log n. Okay, so that ends what I wanted to say about tries, and we're going to whether everything's good. So we can leave off here and continue where we were. We have this two-dimensional text, n by n. We have a two-dimensional pattern, m by m, and what we have to do is find something that can do it in time O of n squared. Now, what is current, what in fact was known, or what can be done with the techniques of Knuth, Morris, and Pratt, is it can still be done in time O of n squared, but only if your alphabets are finite and fixed. So if your alphabet is really the 256 gray levels or something, then you can do it in time O of n squared. Otherwise, your time is going to be, for infinite alphabets, the time is going to be O of n squared log m. And that had been the situation from 1976, more or less, until 1991, when finally this log m barrier was broken and an algorithm was devised that can do two-dimensional matching in linear time, even for unbounded alphabets. And that's the algorithm I'm going to show you. But first, let's see how, with the techniques of Knuth, Morris, and Pratt, you can still do it in this particular time. So the idea is linearization, and that's what we had done. That's what we had done. It's concatenate the rows of the text, or the rows of the pattern, and use string matching tools. And the string matching tool that we used was KMP because this is all we knew. But there's a similar algorithm to Knuth, Morris, and Pratt called the Aho-Corasick algorithm that deals with the same concept of Knuth, Morris, and Pratt, but does a little bit more. And let's see what Aho-Corasick do. So the idea is the idea that we showed. If you take the pattern, and I colored the different strings in different colors, and if you look for all the colors, afterwards, once you find all the colors, meaning you find all the rows, then what you do is you use KMP. You go on the columns and you look for for these particular rows, one beneath the other. So that's more or less what we showed, except for one thing. The reason that our time was n squared m and not n squared and not O of n squared is that we actually looked for every single row separately. And the point is, the Aho-Corasick algorithm allows us to look for all the rows together in time O of n squared. And why? So I'm not going to get into the Aho-Corasick algorithm. This is a short course, and I would rather show as many new techniques as possible. And the Aho-Corasick technique is really not that different from the Knuth, Morris, and Pratt algorithm. But here's what they do. So Knuth, Morris, and Pratt said, if you have a pattern, construct an automaton that at any point when it looks for something and it doesn't find, it goes back to the longest prefix, that's a suffix. That's what Knuth, Morris, and Pratt did. Aho-Corasick said, why do this for a single pattern? Suppose we have a bunch of patterns, which is the case here. So suppose we have a bunch of patterns. Let's construct an automaton where we have, we have the first pattern, and then we have the second pattern in the same way that you do a try. Look for the common prefix of the second pattern and continue where it diverges from the first one. And then look for the longest common prefix of the third pattern with those two. And then look for the longest common prefix of the next pattern, etc. So you have all the patterns sitting in an automaton, but diverging whenever they need to diverge. So as long as you follow the longest common prefix, as long as what you see in the text matches anybody, you will continue with that. And then suppose at this point you get stuck, and like in KMP, and it doesn't match anyone. It doesn't match any of my things. Well, then do the failure link to the longest common prefix that, well, that wouldn't be true, but maybe like to hear. Then the failure link is going to go to the longest prefix that is also a suffix in any of the patterns that matched so far. So it doesn't necessarily need to be for this one. It could be for someone else. But as long as it's a prefix that's also a suffix, go to that one. So the construction is a tad more complicated, but basically what they build is an automaton like that. And so you do the text searching, and in time, O of n squared, you can find anything. But where does the log come in? The log comes in that, in fact, because there are many options, and you don't want to commit yourself, and you don't want to lose anything, since you can't always follow back, because there are now different divergences. So what they do is what Knuth, Morris, and Pratt didn't want to do. They actually look at the next letter and they say, this is the longest common prefix if the next letter is A. This is the longest common prefix if the next letter is B. This one is the longest common prefix if the next letter is C, etc. So they actually construct the full automaton. And because you have a number of possibilities depending on what letter you're looking at, that's where the log comes in, because you need to search, do some binary search on the possibilities. So Aho-Corasick allow us in time O of n squared log m for infinite alphabet and O of n squared to find all these locations, and then we do a KMP and we can find the occurrence of the pattern. And this we can do in the times that we have said. Another option of doing it is by padding with don't cares. Now, yesterday we spoke about don't cares, but assume that you actually linearize the text the way that we had said. Take all the rows of the text and put them concatenate them into one long text. And now assume that you take the pattern, you take the first row of the pattern, and you pad it with n minus m don't care symbols. Then you take the second row and pad it with n minus m don't care symbols, and so on. And you construct a pattern of length nm. But most of it is don't cares. Now, when you take the long text, when you take your long text, which is all the rows of the text concatenated, and you want to find the pattern, well, suppose I have here the first row of the pattern, then I have don't cares, n minus m don't cares, so the second row of the pattern starts here, then I have don't cares again, and the third row starts here, etc. So the don't cares actually align these patterns one underneath the other, or the parts that I care about, and then I can find the pattern in the text using string matching, using linearization. But that actually costs even more, because we still don't know how to handle don't cares. Like I said yesterday, don't cares are not transitive, so we certainly don't know how to do it in linear time. We're going to see probably tomorrow, if I remember right. But we're going to see how to do it, but we can only do it in time n log m. And because the pattern is really long, the pattern is now of length nm, so the time is going to end up being O of n log squared m, which is even worse than the time that we could do it with Aho-Corasick. So yes, this is an option, but it's not a better option. So keep all that in mind. We're going to get back to this in the future. So the pros of linearization is that we can use known techniques. The problem is that we do have a complexity degradation. We have an extra log factor for infinite alphabets if we use the automata methods that we know, and we have even more. We have a log square degradation if we use don't cares. Okay, so what do we do? Now we're coming to the dueling method. The dueling method is inherently multidimensional. So in any dimension that you want to do it, in 2 dimensions, which is where our motivation leads us, but in fact, it could be 3-dimensional because maybe you're looking for some 3-dimensional structure in a folded protein in crystallography or whatever. So it can work for any dimension, and we're going to see. And it's inherently multidimensional. But to simplify the situation, what we're going to look at is going to be, first, we'll start with a 1-dimensional version because that's the easiest. Why think 2-dimensional? Let's see how this concept works for 1 dimension. So we're going to see an alternative algorithm. It's going to be, again, we're going to start with the same problem that we've seen yesterday and today, the Knuth-Morrison-Pratt problem, a string of length n, a pattern of length m, and in time O of n, I want to find all the occurrences of the pattern in the text. But we're going to do it using a different idea, not the longest prefix that's a suffix that Knuth-Morrison-Pratt used. And the advantage of using this different idea is that we're going to see that going to multiple dimensions does not degrade. So we'll start, in fact, in 1 dimension. So we have a new algorithm. And as we did when we spoke about the Knuth-Morrison-Pratt algorithm, I gave you before we started the algorithm and all the proofs and everything else, I gave you the idea. And the idea that I gave you was, do the naive algorithm, and when you get stuck, look for the longest prefix that's a suffix. That's the next shift you can do. That's all you need to remember about Knuth-Morrison-Pratt, because if that's what you remember, afterwards you sit down and you sweat, you can reconstruct everything. So that's the only thing you need to remember. The only thing you need to remember in this algorithm that I'm showing you now is the idea of a dual. And the idea of a dual, we can actually remember that by, again, playing a little bit of a TV game. So suppose we're going to play a game now. And the game is the following. The pattern you see up there. It's ABC, ABCD. That's the pattern. ABCD. The text is here, but I don't know what the text is. However, the object of the game is that we want to work in time that's linear in the text. So I'm not going to allow you to look at the text too many times. So right now the text is unknown. We don't know what's written there. But we're going to uncover places in the text as necessary. But every time we uncover, we pay. So obviously we want to pay the least number of times. So here's the game that I'm playing. I'm telling you that either the pattern starts here or the pattern starts here. One of those two. I don't know which one. And I want you to tell me which one of these two is a liar. So I want to get rid of one of these candidates, because the smaller number of candidates I have, the less number of work I need to do. So let's see, where can we be sure that the pattern doesn't start? So I'm telling you that it may be here or it may be here that it starts. And one of them for sure is a liar. Maybe both are liars. They're standing there and saying, this one says, I am the beginning of the pattern, and he says, I'm the beginning of the pattern. And I want you to at least kill one of these two and say, well, you're a liar, get out of the game. But you're only allowed one peep into the text. So obviously you can say, okay, let's open the text, let's see where's the pattern, and we know who to kill. Well, the point is we don't want to pay that much. All I want to pay is O of 1. I will give you any position in the text that you want. You tell me what is written in that location in the text, and I'll tell you. But then I want you to kill one of them. So let's say that this is index 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So these are the indices in the text. You tell me what index you want me to uncover, and I will tell you what's written in the text, and you'll pay O of 1. But then you need to kill one of them. Okay, so that's the game. So who wants to give me an index? 6. Okay, so there is an option here that says uncover 6. Okay, so I uncover 6 for you, and I tell you that what's written here is a C. Now, who can you kill? Can you kill any one of those two? Is any one of them for sure a liar? So you want to retract your number, right? Okay, so what number do you want to give me? 7, right. I always, between +1 and -1, I always make all these mistakes as well, but yes. The point is, so now you give me a 7, and I tell you that what's written in 7 is A. So who do you want to kill? The leftmost. Right, exactly. So we kill this one. Now, why didn't the 6 help us? Because both of these guys are telling us that the pattern starts here. If what's written here is C, then they both may be right, because if the pattern is A, B, C, A, B, C, D. So if I open the 6, maybe I can kill them both, but I cannot be able to differentiate between them because, in fact, they're not saying anything different about the 6. They are saying something different about the 7, because if he says that the pattern starts here, what he's saying is that I want to see in index 7 a D, because that's what the pattern says, 1, 2, 3, 4, 5, 6, 7. So the leftmost says, I want to see a D in index 7. What does the rightmost guy say? He says, well, I want to see an A in index 7 because I start here. So this would be 4, 5, 6, 7. So I want to see an A. They don't expect to see the same thing in index number 7. And therefore, if I uncover index number 7, all I pay is O of 1. But in this O of 1, I can already tell you that the pattern doesn't start here. Now, if I had a method in O of 1 where every time that I open a place in the text, I kill off a potential candidate, then in O of n, I would kill off all the bad ones, and I would be left only with the good ones. So if I had a way of doing that, I would be done in linear time. Now, it doesn't work quite as easy as that, exactly in the same way that with Knuth Morris Pratt, we had to do some massaging. So we're going to need to work a little bit harder here. But the idea is the idea of the duel. This is what they do. The two of them are going, any two people or any two indices in the text, where one of them claims, I am the one who starts the pattern. The pattern starts here. And the other one claims the pattern starts there. We do a duel, exactly like in the movies. I asked you about movies yesterday also, and people didn't know. But Western movies, I mean, this is Bollywood, and Bollywood country, and I know Hollywood mostly. But in Hollywood movies, did any of you see any Westerns like Clint Eastwood or the Duke? Okay, so what do you see in these Westerns? You see a bad guy coming to town and saying, well, this is my town. And then you see there's a sheriff or something, and he says, no, this is my town. So then they have a duel. And the duel is at high noon. In all the Westerns, the duel is at high noon. Why is it at high noon? Because in the movies, they're very fair. And so when the sun is exactly in the middle of the sky, there's no advantage to any of the shooters. because the sun isn't in anyone's eyes. So the duel is always at high noon. So the sun, that's in the movies. I'll tell you in a moment what happened in real life. So the sun is not in anyone's eyes. And then you see them at a distance, and you see one of them standing like that, and the camera focuses on his eyes, and he's squinting, and the music goes, ta-ra-ra-ra-ra, ta-ra-ra. Then the other guy is standing on the other side, and the camera then focuses on his eyes, and he's squinting, and the music, ta-ra-ra-ra-ra, ta-ra-ra. And then the camera moves back to this guy, and you see his gun hanging here, and his hand like that, and it focuses on his hand, ta-ra-ra-ra-ra, ta-ra-ra. And then again, focuses on the other hand of the other guy, and then a single shot of one is fired, and the bad guy drops down. So this is the classic duel. And that's what we had here. So we had the two of them. He says, this is my pattern. He says, this is my pattern. A single shot, that was the shot, the duel, and one of them drops dead. So thus the name duel, and because of Hollywood. But let me tell you what happened in the real world. Now, in the real world, there is no documented case at all in the history of the West of a duel at high noon. But not only that, there's no documented case of two people standing like that and having a pistol fight because their guns were crappy and they didn't shoot straight. And you couldn't, even if you were the best shot in the world, the gun could have blown up in your hand or whatever. It wouldn't shoot where it needed to shoot. And so they didn't do that. Not to say that there were no murders in the Old West. There were a lot of murders. But they were done in one of two ways, either with a rifle. The rifles were very good. And if you wanted to kill someone, you would ambush them. You would sit there, and when they go by, you shoot them, okay. So that was done plenty of time, not the way that we use it in our algorithm. Another thing that was done is with pistols, yeah, but they were usually drunk. So they were drunk in a bar, and one didn't like the other, so he took out his gun, stuck it in the other guy's stomach, and pulled the trigger. Anyone can do that. You don't need to be like Wyatt Earp, the legendary sheriff, in order to do that. Now, there is one story that is documented in the history of the Old West where they actually had a shootout with pistols. That was in Tucson, Arizona. No, in Tombstone, Arizona. The shootout was the famous shootout between the Earp brothers, and I think Doc Holliday, the famous outlaw, was with them. Except in those days, people used to change their hat from outlaw to sheriff whenever. So you never know. It depends on the time if someone is really a lawman or an outlaw. But in those days, the Earp brothers and Doc Holliday, they fought a bunch of other people. So there were 3 against 4. And in OK Corral was the shootout. Now, the size of OK Corral is about 1/3 of the size of this room. And because it was in the middle of town in Tombstone, and they used to keep horses there when people rode in or out. So the corral was where they corralled horses. It was called OK Corral in Tombstone, Arizona. So the Earp brothers and Doc Holliday were in one side, and the bad guys were in the other side, and they were more or less this distance from each other. And they all took out their pistols, and they shot at each other for 10 minutes. At those 10 minutes, most of the bad guys were dead, and somehow, miraculously, the good guys were alive. So this is the only shootout that happened. There were a lot of shots fired. Quadratic number, maybe even, I don't know, n cubed. So this is not good for our example. That is why we went to Hollywood, and what we use is a shootout in the classic Hollywood sense that never happened in the real world. Now, other people who are less of a less colorful imagination call this the witness table method, not the duel method. I think duel exactly speaks to this, but they call it the witness table method. And the reason they call it the witness table is that they say, well, why are you so bloodthirsty with all the shooting and everything else? But I'm saying it's not bloodthirsty, it's Hollywood. No one dies in Hollywood. It's just the film. So it's not really bloodthirsty. This never happened. But those people don't even want the assemblage I mean, these are the people that don't even watch cartoons, because in a cartoon, you know, all these bad things happen to the cartoon characters. They blow up, and they say, no, this is too violent. So, but you know, it's movies, and we remember algorithms better with movies. But they say witness table. Why? Because they're dry. They're like lawyers. They say, okay, we have these two people, and they're giving testimony. They're witnesses, and they're saying, well, he says, here's where the pattern starts, and this one stands in court and says, my testimony is that this is where the pattern starts. So they say, okay, so let's see. So they bring out some guy with a powdered wig, and he opens up the witness table, and he says, well, there's an A here. So we say, well, indubitably, if there's an A here, this witness is a false witness. Please take care and remove him from my courtroom. So they call it the witness table. It works, but how can you remember an algorithm this way? So we'll stick with the dual. All right, so, but what do we need in order for this thing to work? What we need is this witness table that we spoke about, because we want to be able to eliminate people fast. Oops. To eliminate liars fast. Actually, why am I taking it down? I'm going to write in a minute. So candidates claim, here's where the pattern starts, or here is where the pattern starts. We want to be able to show what in the text do I uncover in order to be able to get rid of one of them. Now, how is it going to be? Well, first of all, these guys can't be too far away from each other, because if there's nothing in common between them, there's no way that I can tell who is bad with a single shot and be 100% sure. So obviously, they need to be close enough. They need to be within O of m of each other in order to be able to even have a common overlap, an overlap area where both of them actually expect to see something. And then in that overlap area, we need to make sure that one of the locations in that overlap area is different. Now, because we're talking about these candidates being within m of each other, so the witness table does not need to be more than of length m. And why? Because I'm going to say, all right, let's adjust everything so that the leftmost is assumed to be in index 1. Okay, so it doesn't matter. I mean, whatever is to the left of them doesn't matter anyway. So let's assume that that's the index of the text also. That's where everybody is. Everyone starts. So the leftmost candidate starts at index 1. And then the rightmost candidate, the furthest away that it can be, and we have a chance of saying something, would be at index m. So therefore, our table is going to say this is where the leftmost candidate starts, and this is where the rightmost candidate starts in index I. So every index is the index of the rightmost candidate. What we're going to write in the index of the rightmost candidate would be, what index do I need to uncover in order to annihilate one of them? So, therefore, let's move it up and put it all up. So we have this table, and what we're going to write in this is our data structure. It's the witness table. So WI is going to say is going to be K if PK is a witness to a mismatch. In other words, suppose that what was written here is m minus 1. Okay? So it means that if I go to position m minus 1, so this one is 1. We're adjusted to the start of 1. So if I go to the text in position m minus 1, I open it up, then it's going to tell me either this one or this one is a liar. So that's what we're going to write. Now, the one problem that can happen is the problem that I am sure all of you thought, but you forgot already, that lo baishan lamed, so you're too polite to say. But what happens if they agree on the overlap? So all this is assuming that the overlap, I can find one position where they overlap, where one of them wants to see A and the other one wants to see B. Clearly, both of them can't be right, so if I uncover that, one of them goes. But what happens if they happen to agree on the overlap? Then I can't do it. For example, in this example that we had before, ABC, ABC, D, no. Suppose we had ABC, ABC, okay? So if one person says here starts the pattern, and the other one says that the pattern starts here, what's their overlap? The overlap is this. And they both expect to see exactly the same thing. So obviously, there's no way of doing anything. Now, of getting rid of one of them. Now, in the dual simile, so if you're looking at a Hollywood movie, what it would be tantamount to doing is that someone comes to town and the sheriff stands there and says, I'm the sheriff of this town. And the other guy stands in front of him and squints and says, you are the sheriff of this town. Well, there's no reason to fight. They agree. So in this particular case, they agree. There's no reason to fight. Now, in our case, it's bad when there's no reason to fight. But if there's no reason to fight, our algorithm needs to account for that. So the algorithm is going to put an asterisk in the witness table in a location where I cannot kill one of them. So the witness table, to recap and to summarize, the witness table is going, if sliding the pattern to position I actually gives us an overlap, there's going to be a asterisks in the witness table. But if there is a mismatch in the overlap, then we're going to put there an index of one location in the overlap where they disagree. And by the way, any position in the overlap where they disagree is right. So we can put here many possible numbers. If there are many places where they disagree, we can put any of them. We can choose it at random. We can use the leftmost one. We can use the rightmost one. In the application that I'm going to show you, the one that for exact matching, it doesn't matter which one you choose. But there were applications where this idea of witness table was used, where you necessarily want to choose the rightmost one, and that helps you, because if you choose any other thing, you may miss something. So again, if you can't choose anybody to kill one of them, you put an asterisk because it means they agree. And if you can, you put an index of a witness that says one of them is false. But for us, it doesn't matter which one. Let's see, I think I have an example here. This WI, okay, let's look at an example, I think. And at that point, yeah, here's a beautiful example. Okay, so our pattern is AABB, AABB. Our witness table, obviously, is going to be of length 8. What do I write in W1? What does W1 even mean? W1 means that the leftmost and the rightmost are both positioned in the same location, in location 1. Is there any difference in the overlap if both of them start at the same place? They both obviously have to see the same thing, so we cannot kill one of the two. And that's there just for completeness because this is not a useful case. We never actually do a duel between two people in the same location. Okay. What do I write when, so what's in W2? W2 means that the distance between, that if the leftmost one is here, AA, BB, AA, BB, then the rightmost one is here, AB, no, not AB, AA, BB, AA, BB. Let's write this nicely so you won't be confused. So W2 means that this is how you align them. And the question is, what do I write in the witness table? Well, I'm not going to write, obviously, 2 because they both expect to see the same thing. But can I write 3? Of course. So I can write 3 because in 3, the leftmost wants to see a B, the rightmost wants to see an A. So I can definitely write a 3 here. Of course, as I told you, if I, for our purposes, I can also write 5. I can also write 7. So 3, 5, or 7. Any of these would be okay. Because it would mean that in one shot I can tell who's lying. Okay, what do I write in 3? Star. Does everyone agree? Because in 3, it means that now we have one more shift. So we have AA. Sorry, no, it's not a star. My bad. We have AA, BB, AA, BB. So in 3, we can write either 3 or 4 or 5 or 6 or 7 or 8. In location 3, everybody wants to see something else. So 3, we can write anything. Let's just write 3. What about 4? Give me a number. 4. 5? 5 is a star. 6? 7. 7 can also be 7. And 8? 8. So this would be the witness table for this particular, or this could be one witness table, what we wrote here. But obviously, any number, any k that kills one of them would be good. Okay, now is this clear or there is still, it's clear, good. So what we have at this point is, in our hands, is an idea where we can construct a witness table, and the witness table basically lets us, when we do a duel between two elements, it can tell us either that they both agree on the overlap, or one of them is a liar, and then we kill him. So that's what we have so far. And now comes the algorithm itself. So the scanning, the text scanning algorithm. The text scanning is going to say the following. Okay. You know, this machine actually spoils me unbelievably because for some reason, all the machines in my university are so slow to go up and down that I try not to do it too often. And this is just brings me back to the happy days of the manual O of 1 up and down. It's unbelievable. So what's the algorithm going to say? The algorithm has two stages. It has a dual stage and a verification stage. Because remember, what the dual does is it doesn't really tell you for sure that any particular location is a location where the pattern starts. But what it can tell you for sure is that some locations the pattern doesn't start. So you're going to have a dueling stage where all the conflicting sources are going to be able to eliminate one of them. So you're going to kill, and hopefully you're going to remain with a small number of candidates. And that small number of candidates you're going to verify. And let's assume now, for the sake of ease and simplicity, that you're even going to verify it in a naive way. In other words, you say that here a pattern starts. Let's check if really that's where the pattern starts. We'll check all of them. Now, why is verifying it in a naive way not so scary? Because suppose, for example, that we were able to eliminate all but n over m, let's say, candidates. If there were even less than that, no problem. But all the candidates that remain that were not killed yet is n over m. Now, that's the number of candidates that we have. Even if I naively verify each one of them, the time for verification is O of m. So I still have an O of n time algorithm, which is what I'm looking for. So the idea of killing bad guys is good, because if you really can assure yourself that you killed a lot of them, or at least as many, then you're done. Now, we'll see that unfortunately we cannot always guarantee that we kill a lot of them. But we'll see that if we don't kill a lot of them, we have something else up our sleeve that we can do. But let's go one by one. So we said here, step 1 is eliminate, and we eliminated by the duels. Step 2 is the verification stage, and verification is what we're going to leave that to the second stage. We'll start by eliminating all the conflicting guys. Now, in English, it actually sounds nice. It's the elimination stage and the verification stage. In Hebrew, there's a in Semitic languages, there's a guttural sound ah that appears in many words. So many modern Hebrew speakers actually got rid of it, but you can hear it in Arabic because Arabic has a lot of the guttural ah. Now, the conflict stage, where you actually conflict them one with the other, is called, or the dueling stage, would be called in Hebrew, shlava aimut. So, aimut. But verification would be imut without the guttural. So it would be aimut versus imut. And so if you don't actually worry about speaking with the guttural ah, then it would sound the same, which is a big cause for confusion, and also causes a lot of jokes, which I'm not going to be able to tell you, because this joke is a very language-specific joke, and you would not be able to laugh, and there's nothing sadder than telling a hilarious joke and having the crowd look at you stony-faced. So therefore, I will not. And to explain a joke is actually very pathetic. So I'm going to skip this joke. If you want to hear it, try to find in the internet the Hebrew version of this lecture, and that joke is probably there because it really fits right here. So we have the dueling stage and the verification stage. So let's start with the dueling stage. Obviously, we can start by testing all the pairs and making a duel between all of them and killing one. Now, all the pairs is O of n squared. That's out of the question. We're certainly not going to do that. But you're going to say, well, we obviously don't even need to try O of n squared. It's enough to do O of nm. But O of nm is also stupid because we have an O of nm algorithm. And so we want to do better than that. Why O of nm? Because for every area of n, we want to see we can eliminate. Anybody who is further than n away, we don't need to dual them. So every person has to dual only the m elements within range m of itself. So the first one needs to do m duals, the second one m, the third one m, and we don't want to do all of them. Mm-hmm. Then we come to the verification. Yes, I haven't answered the potential question yet. Certainly don't want to do it that way. However, notice that it doesn't even seem like you need to do it that way, because if you dual the first element with all the m elements that are within its range, then you already dualed the first and the second, the first and the third, the first and the fourth. Then all these other guys don't need to dual with the first. And so somehow these duals, once you eliminate somebody, he doesn't need to duel anybody else because he's dead. It doesn't help. So we have to utilize the fact that if you have a duel and someone dies, then he doesn't participate in any future duels. So what we need is a good algorithm, a good efficient algorithm that is going to allow us to do all the duelings, all the duels where we can kill someone, and do that in linear time. So that's the next thing that we're going to do here. And so let's go to the dueling algorithm. So here we have these two guys in the duel, and let's see how the algorithm works. So so let me again reiterate what this particular presentation is going to show. So this presentation is going to show that in linear time, in time O of n, we'll be able to carry out all the duels where two conflicting elements, one of them can be eliminated. So at the end of which, so after this O of n time, we're going to be presented only with potential candidates that agree with each other on everything. Because if any of them disagreed on an overlap, one of them would have been eliminated by this algorithm. So what we're showing now is an algorithm that in time O of n does all the duels that need to be done in order to present us with an output of candidates that agree, a bunch of yes men. So they agree. Whatever anyone says, everybody says, yeah, yeah, I. The I's win. So that's what we're going to do. There's one important data structure that we're going to use, and that's the list of potential candidates. So we're going to basically have a list of the potential candidates. So if this is the text, and these are the indices of the text. So in this list, we're going to keep the indices of all those who are still potential and are still alive. So all the candidates who are alive are in this list. Anybody who was got rid of is not going to be on the list. We don't care. Goodbye. Thing of the past. Now, the rightmost element in this list of potential candidates is going to be pointed to by a pointer R, and the new element, because we're going to go from left to right, the new element is going to be pointed to by the pointer n. Now, why is there a distance between r and n? Because presumably the algorithm already killed all of these guys. So these guys participated in duels, were unfortunate and lost, so they're not potential candidates. So this is the last potential candidate. This last potential candidate is going to have to duel with this guy, with the new one. And then they're going to duel, either they both agree or one of them dies, and so on. So I'm going to need to basically go from left to right and show you how I take care of updating this data structure. So at the end, what's left in the data structure are exactly the candidates that I want them to be there. All those who agree with each other everywhere. Now, there's also, so I'm going to now start the algorithm. That was the only data structure. But before I start the algorithm, I want to make sure that there's something else we understand. I am going to, throughout this algorithm, say dual between I and j. So in this, as I described to you, I will say many times, dual I and j. So I and j are going to have a dual. What do I mean when I say that I and j are going to have a dual? It means that I am going to look at index, okay, and that's with the assumption, assume without loss of generality, of course, that I is less than j. If they're equal, there's no, I never do. But if, let's assume now that I is less than j, and we do a dual between them. So what I mean is the following. Go to the witness table. So it's basically saying that I is going to be the leftmost candidate, so it would be 1 in my witness table. And so j is going to be j minus I plus 1. So j is going to be the position j minus I plus 1 in the witness table. In other words, I juxtapose the, I assume that the text position of the leftmost I is in 1, and therefore I need to see what is the relative distance between j and I, and where would j be mapped into on the witness table. So I look at j minus I plus 1, and that's where j would be on the witness table if I is mapped to 1, okay? So in other words, when I say dual I and j, what I mean is go to the witness table and look at location j minus I plus 1 and see what is written there. And if what's written there is a star, then you're going to say both of them survive the duel because none of them dies. And if what's written there is, let's say, k, then what do? I need to look at position k, but relative to I, right? It's not k relative to 1. It's k relative to I. So in short, I need to look at position I plus k minus 1, which is going to be the kth location away from I. Okay, so I plus k minus 1. I'm going to look at that text location, and I'm going to ask, does it want to see P? So what's written there is k, right? So I'm going to say, does that want to see pk? If it's equal to pk, it means what? It means that I is right. And at that point, I kill j. And if it's not equal to pk, then I'm going to kill I. Okay, so I'm going to say now, throughout this algorithm, many times dual I and j. And what the dual means is that whoever needs to die, die. And this is what I will mean. So I didn't write this down specifically. As you can see, when we go on and on, I write less things down specifically. But if something is not clear here in the detail, stop me, because I don't want you to go back and say, what does it mean a dual? What does it mean a dual? Okay? Right. So what I'm going to show you now is an algorithm that is going to do O of n duals, and at the end of this O of n duals, it's going to have a list of potential candidates that all agree with each other. Okay, so how do we initialize? Well, we're going to add 1 to the list. The list is empty. So, tabula rasa. You go into an empty territory in Wyoming, and you start a town, of course you're the sheriff. Who's going to say no? So we put 1. He's in the list. He's a potential candidate. There's no one to say no. But this is what happens. You start a town, so someone else shows up. So 2 shows up, and 2 says, you know what? You may have been the first one here, but I want to run things. So they do. So that's what we're going to do, is to make the first duel. But at this point, we're still not making a duel. We're just initializing. In the initialization, 1 is in the list, and R points to the rightmost element in the list, and N is the one who comes, and obviously our algorithm is going to basically loop on duels between R and N. That's what the entire algorithm is going to be. So that's the initialization. And then here is the main loop. While N minus the new character is greater than or equal to M minus 1, we're going to get into the loop. Otherwise, we're done with the algorithm. Why are we done with the algorithm? Because if the new guy doesn't even fit, because if this length is equal to M minus 1, then there's only M minus 1 positions for him. So obviously, he's no threat to anyone if he doesn't fit. It's like Monty Python and the Holy Grail. Did you guys watch that movie? Anyone? That one I really recommend. It's a classic. It's a classic English humor movie. So I really recommend it. However, if any of you still harbor any ill will towards the British, then don't watch it. I mean, they were also the colonialists in Israel, and we got independence from them more or less at the same time. And they threw my father in jail for 6 months. So I don't like British either. But their humor is interesting. So Monty Python and the Holy Grail is one of the best English humor that you can see. And even if simply for that, it's a classic, it's worth looking into. But there's a guy who like fights and he keeps losing limbs because he's fighting a duel with swords. And he keeps losing limbs. And he says to the guy that he's fighting with, "Come back and fight like a man." He says, "What? You don't have an arm." He says, "A mere flesh wound. I can fight with the left." And then he chops off his leg. No, then he chops off his left arm. He says, "All right, now you're." He says, "No, a mere flesh wound." And he runs after him and kicks him. So he chops off one leg, and he keeps saying a mere flesh wound. So here, we don't allow these guys with mere flesh wounds. If he doesn't fit, he's not in. He's not fighting. Okay, so this is the main loop. And as long as the new guy can fit, we loop. Now, when we're going into the loop, there's also another extreme case that we need to worry about, and that is what happens if the new guy is now too far from the right guy in the list. At that point, we also can't fight. So the first case that we're going to say is what happens if n minus r is greater than or equal to m. That means that the candidates are too far. They can't fight. But if they can't fight, what does it mean? It means that we're going to add n to the list because there's no one to say that he doesn't belong there. So we're going to add him to the list. N becomes the new right because he's now the rightmost in the list. And the new n is n plus 1. So that's a border case that we need to consider if we're writing an algorithm. And at this point, we end the border case. Okay, so, oops, what happened here? So what it means, yeah, I have nice animations in this one. So what it means is that n is too far from r. There's more than m between them. We can't duel. So then what happens is we're going to add n to the list. He becomes the new r, and the new n is 1 over to the right. So this is this case. And now we finally come to the main loop. The main loop is when the candidates are within mutual range. And the main thing that happens in the main loop is that we duel between r and n. And when I say duel r and n, I explain to you what I mean. And you know what that means already. So we r and n duel. And then there are 3 cases exactly that can happen. Either n dies, or r dies, or both of them live. So these are the 3 cases that we need to consider. And we're going to show what we do in each one of these 3 cases. So case 1, n dies. N dies is easy. Remember, who is n? N is the newcomer, Johnny come lately. He dies. Fine, so he dies. Get him out there. Get him out of here. They always have these old men who, in Hollywood, who carry the dead guy out of the middle of the street, and then there's a new guy that comes in, n plus 1. And we go to end while, because if we're going now to start of the loop, if n plus 1 is too far, then we know what to do already. And if it's not too far, then we duel again. So in short, we're done. I mean, we know what to do in this case. So in the animation, n dies, so he's out of there. That's the new n. And we go back to the, sorry, oops. And we go back to the beginning. We have the new n. Now, the second case is when r dies. So if r dies, we remove him from the list. However, note what happens. Because if we remove r from the list, the end is not over. Because in all these Hollywood movies, the sheriff also has a deputy. So if the bad guy killed the sheriff, isn't there a song? I killed the sheriff, but I didn't shoot the deputy. So, okay, so they shot the sheriff, and the sheriff is dead, but now the deputy comes up and says, what? You think you can tromp right over this town? You now have to go through me. So we need to worry about that case. And therefore, what we do when r dies is we remove him from the list, of course. And if the list is empty, this is like one of these border cases also. If the list is empty, then obviously n becomes the new r because it's the only one left standing. And n plus 1 is the new n, and we keep going. But it could be that the list is not empty. At that point, r is going to be the previous element in the list. That was the deputy. And we're going to go to n while because the deputy is going to say to this newcomer, well, you got to go through me. So they're going to need to duel again in order to see whether the new guy deserves to be there or not. Okay, so now, why does it make sense? Because remember, we want at the end to make sure that whoever is left agrees with each other. So here, if n killed r, I still don't know if he agrees with the other people. So he has to go through the deputy. Now, if the deputy kills him, okay, fine, because the induction is that everybody in the list already agrees with each other. Okay, so again, what is the animation here? R is fighting with n, and r dies. So he is removed, and that's the new r. And so if in order for n to actually be added to the list, he needs to make sure that he also agrees with r. And we don't know if he agrees with r unless we check it out. So we duel, and we see if they agree. But that will be the next. So we're going to the end, and in the next step, either they're too far and we know what to do then, or if they're not too far, they're going to duel again, but all that is for the future. But this is the result of case 2. And case 3 is the case when we duel, and there was actually an asterisk because no one died. So if no one died, then we're going to add n to the list because no one died. And n goes to n plus 1, and we end the loop. So we do the duel, and it's a love fest. They agree. So fine. So we put n in the list, and the new he becomes the new right, and we move over one. Now, at the end of the algorithm, all the elements in the list are potential candidates. That's what we claim, which we're going to need to prove, because are we sure that we didn't miss anything, that maybe somehow one of them is not a potential candidate? And we also claim that all of them agree with each other. So we're going to need to prove that they all agree with each other, and we're going to need to prove that the time is O of n. So that was the dueling algorithm, and let's see the proofs of the things that we're claiming. In fact, in order to make sure that the time is O of n, we don't know that the time is O of n. As long as we move to the right, that's fine, because there's only n to move. We never move to the left. The problem is sometimes we continue doing duels and staying on the same spot. When? If we do a duel between R and N and R dies, then N is then going to do a duel with the predecessor. And then maybe the predecessor dies and N is going to do a duel with the one before that and the one before that. And if there were M predecessors or O of M predecessors within M distance, there are going to be O of M duels before we move over to the right. So here we also have an amortized argument that we're going to need to take care of. When you're getting stuck, yes, you're getting rid of potential candidates. We move, we do a duel and we move. We can't say that because sometimes we do a duel and we stay and do another duel and another duel and another duel, and only then we move. Okay, but you're right in the fact that we feel that the amortization will work, because if we dueled M of them, then the next guy can't duel M because you already killed all of these guys. So that's what you were trying to say before. I mean, so if I dueled and I killed all these M guys, the next guy is not going to be able to duel with M people. They're dead. All the M preceding guys. The work was done by the guy before. So again, there's going to be the amortization argument that we're going to need to do in order to prove that indeed this is O of N. So here's how we're going to prove it. So the easy thing is what we have established, that as long as the new location is eliminated, we only go forward. So as long as N dies, there's only O of N. So let's count, let's do our counting, not by how many duels we make, but by the result of the duels. So let's see, how many duels do we do where N dies? How many duels do we do when R dies? And how many duels do we do where there's a star? So if the sum of all of them is O of N, then we're done. So that's the count that we're going to do. We're really not going to count duels, we're going to count results. So as long as N dies, we go forward, which means we know that there's only O of N duels where N dies. Can't be more than that. Okay. Now, the problem is that if the old one dies, we do another duel and another duel and another duel. However, remember the old Ian Fleming book, You Only Die Twice? Well, here you only die once. Because if you do a duel and R died, he's not going to do any other duel. So no element can participate in more than one duel in which it dies. It can participate in many duels in which it lives, but it cannot participate in more than one duel in which it dies. Because once you're dead, you're dead. You're out of there. You don't duel anybody anymore. So let's do, and this is something else that we can go back to the Hollywood movies and to the Westerns. Because in all these Westerns, before the duel, there's the coffin maker. He usually has a top hat and he wears a black overcoat. So the coffin maker, he runs over and he measures the two of them, the height, because he needs to build the coffin for the dead person. The question is, who pays for this coffin? Well, the winner is obviously not going to pay for the coffin because he just won. So what does he care? He wanted to kill the guy. He's not going to pay for his coffin. So the dead person pays for the coffin. So here's the thing. For every duel, the person who pays for that duel is going to be the dead guy, like the one who pays for the coffin. In other words, how many duels can there be in which an element dies? Not more than N. Because once you die, you can't participate in another duel. And when you die, you pay for that duel. So every duel is paid by the person who died. Therefore, forget about duels where N dies. Any duel where N dies or R dies, the sum of them can't be more than N. Because if the dead person pays for the duel, and no dead person can participate in a duel, then the number of duels in which anybody dies is O of n. It's not more than that. Okay, so we're getting somewhere. We're making progress. We only have O of n duels where the result is catastrophic. But now comes the question, how many duels do we have in which nobody dies? These are all the asterisk duels. So let's see what happens there. Okay. It doesn't even say that, but so I will say it. So what happens in a duel where nobody dies? In a duel where nobody dies, what did we do? We moved over to the right. We added the new guy to the list, and we say, this is bliss. So let's just move over. So how many duels can there be in which no one dies? No more than n, because in every such duel, we move. And we cannot move more than n. All right, so here we are. The time of this algorithm, the amortized time, and this was even easier than proving the amortized time before, because here we just charged the death to the dead, and at that point we're done. So we don't even need any potential argument. All right, so the time is linear. What about correctness? So let's look at what happens. There are really three cases that happened in the algorithm, and we want to make sure that we didn't miss anything. So these are the candidates. I even numbered them here. And the new source I put in a square. So the new source, the n, duels with 3, which was the r in our in the algorithm we saw in the presentation. Our inductive assumption is that all of these guys all agree with each other. In other words, up until now, we did not add anyone to the list who has a conflict with anyone else. So that's our assumption. Obviously, it's true when we started. So now we have the inductive hypothesis. Everything is true up until now, and then there's the new guy. So if the new guy dies, no problem. Everyone still agrees with each other. The new guy didn't agree with one of them, so his place does not belong there. He is now in the happy hunting grounds in the sky. So he's not with the list of potential candidates. That's good. Now, if this one is eliminated, we're also okay. Why? Because what did we say we're going to do? We're going to then check the new guy against number 2. See, remember, that's what we said that we do. In case the sheriff dies, then comes the deputy. So 2 is the deputy, and we're going to check against him. And if the deputy dies, we're going to check back until finally they're too far from each other. And then everything's good. They still all agree. Because anybody who's in another town obviously agrees. There's no... Or if the new one dies, then by induction, whoever is left is agrees. So as long as people die, we're okay. Same thing as before. As long as people die, our invariant of everyone in the list agreeing with each other is kept. But the question is, what happens if if r and n, in this case 3 and the square, we do a duel, we get an asterisk, they agree. What did we say we do? We add the square to the list. As we say in Hebrew, mazel tov. Good. So mazel tov means good luck. That's like congratulations. You say that when people get married. Good. Congratulations, you're added to the list. But why? I mean, why did we so blithely, willy-nilly add him to the list? Just because he agrees with 3? So he agrees with the sheriff. Does he agree with the deputy? Why didn't we confront him with the deputy and see whether he agrees with him or not? Now, okay, so we say, all right, let's confront him with the deputy. But if we do that, our algorithm is not going to be linear time anymore. Because why did we say that it was linear time? Because either someone dies, or if he doesn't die, we move on. But if we conflict him with the deputy, we're not moving on. And then who pays for that? Huh? No one died. Who pays? So we're in trouble. So for the sake of time, we said, all right, let's add him. But then, fine, for the sake of time, just add everyone in. But if the algorithm isn't correct, then how can we do that for the sake of time? So here, we're stumped. We're stumped until we remember. What did I tell you yesterday about the Knuth-Morris-Pratt algorithm in White's linear time? And I told you that all the linear time algorithms are linear time because of something that even if I wake you up in the middle of the night, you remember, starts with a T. What is it? Transitivity! Exactly. Here's another name for me now to remember. So what's your name? Jayesh. Okay? All right. So, Jayesh remembers. Transitivity. So, what does it mean to be transitive here? If all these guys agree with each other, it means that 2 and 3 agree on their overlap. If 3 and square survive the duel, it means that they agree on the overlap. So let's draw these overlaps and see. Whoops. Let's draw these overlaps and see what happens. So here is 2, here is 3, and by induction, they both agree on the overlap. So this is their overlap, and what's written here is here. All of these are the same. That's inductively. Now we have the new dual between these two, and they agree on the overlap. So this is their overlap. Now my question is, do I even need to check whether 2 and nu agree on the overlap? Obviously not, because their overlap is part of the overlap of 2 and 3 and of 3 and square, because he's even further from 2 than he is from 3. So his overlap obviously is included in it. That's his overlap with 2. So 2 has a bigger overlap with 3. 3 has a bigger overlap with square. But the overlap of 2 and square is included in the overlap of 2 and 3 and of 3 and square. So we have transitivity. This is equal to this, and this is equal to this. Therefore, this is equal to that. No need to check. And that's why we were able to have a linear time number of duals, because if everybody is alive, it means that he agrees with everybody because of transitivity. And if you want to use a dueling algorithm for any relation that doesn't have transitivity, it's not going to work because you're going to need to duel everyone, and you're going to have NM duels. So for anything that's not transitive, as I already intimated to you yesterday, we're going to need to have yet another idea for the algorithm. But no one in the world knows how to do a linear time algorithm for matching with a non-transitive relation. However, fortunately, equality is a transitive relation. We can do O of n duals. So here's the result of step 1. We have a bunch of candidates on the text, and all of these candidates are pairwise consistent. They all agree with each other on the overlap. There's really, you cannot phase anybody. I mean, if you say, I'm good for him, you're good for everyone. There's no one who's going to say, well, what about me? What's good is good for everyone. So that's what we get. Now, so the meaning is clear, that if it starts at 2 overlapping sources, then they must agree on the overlap. So now we come to the verification stage. How late can I go? There's not going to be hordes clamoring at the door saying this is the next class and get out of here? Okay, fine. All right, so you lose because there are no hordes out there. You're going to have to sit and listen to the verification stage. Thought was, let's do a brute force, because start at each source, check all the elements. If they're far away from each other, this is good. However, they may not be far away from each other, and the overlaps may still cause the time to be mn. Let's look at this example. And at this point, you're really, this is going to be like a little exercise on what we said so far. So if my pattern is A, what is the witness table going to look like? I know it's easy. Yeah, it's all stars. You're going to be seeing stars. Because no matter how you shift it, everybody agrees. So the witness table is going to be all stars. If the witness table is all stars, then how does our potential list look? Like you see there. Because the first two elements are a star, so we add the second to the list, and then the third agrees and he adds to the list, and the fourth agrees and he adds to the list. So we add them all to the list. And our list of potential candidates is everybody. Wow, what a love fest. Everybody is potential, everybody's good. But the problem is, if everybody's good, we haven't done anything. Because now, if we're going to, via brute force, check them out, then our time is nm again. Whoops. But the fact that all of them are candidates doesn't mean that we have to check that it's just a random number of elements that I'm saying all of them are candidates. The fact that all of them are candidates actually means something. What does it mean? That they all agree on the overlap. Which means that if I start with this guy, and I check, and I verify him, and he was completely verified all the way to the end, do I need to verify the second guy from where he started or from where the first guy ended? Only from where he ended, because they agree on the overlap. So I don't really, so even in this particular case, if I don't just do it totally stupid, if I think a little bit about the fact that they all agree on the overlap, then I may not need to check everything. Why? Because what's important to remember is that we have come to a situation that's very unique. Every position in the text is either good for everybody, because everybody wants to see the same thing there, or it's bad for everybody, because nobody wants to see that there. But there is no disagreement. Now, this is a very powerful thing to say, because what does it mean? It means that every text position is either good or bad. How many text positions there are? There are only O of n positions. So if I somehow can pinpoint and say for every text position what it is that is good for it, then just go through the text in linear time, and every place that's good, you say it's good. Every place that's bad, you say it's bad. And your time is O of n to find out what are the good and what are the bad places in the text. At that point, what's good is good for everyone. What's bad is bad for everyone. So it seems like we really have enough information here. So it seems like we have enough information here to actually figure out some formula in order to verify up to a point and then know whether I continue or discontinue or that sort of thing. The point is, yes, we have enough information and we can figure out such a formula, except, and that formula isn't even going to be that hard, but I'm not going to do it because historically, this is not what happened. Historically, the algorithm that I'm showing you never appeared anywhere. This algorithm that I'm showing you is just the one-dimensional version of a two-dimensional matching algorithm that we're going to start with already tomorrow. But the two dimensions we're not going to do today. But this is the one-dimensional version of the two-dimensional algorithm. And in two dimensions, to start saying where is the beginning, where is the end, and who is good for whom, because you now have candidates all over the place that overlap each other in all kinds of weird rectangular ways, you really get stuck. The formula there is really hard. And so we actually had a problem with that. And so we sat on that After we finished everything, we sat there and we said, how do we do that? And then happened one of these things that actually you read about, but it rarely happens. I actually woke up in the middle of the night with the solution. And so I ran to the computer and I wrote it down so that I won't wake up in the morning and forget it. So I ran to the computer and I wrote down the solution. And the solution is so simple that it's almost painful. The solution is the wave. Now I'm going to have to tell you something. Now we spoke about movies, we spoke about literature. Now we're going to speak a little bit about sports. So I'm going to need some props for this. So here, I'm going to put a few chairs here. And I have to keep you on your toes, right? So I'm going to put a few chairs here. And now assume, let's bring this one also. So assume that these chairs are actually chairs in a stadium. And so the crowd is sitting here and watching in your case, a cricket game. Okay, in America it was clearly a football game. In Israel it was basketball. In Russia it would be chess. But okay, so here are the audience, and they're watching their favorite sports team playing, and they want to cheer them. So one of the known cheers is called the wave. What does it mean? I don't know. You probably saw it. They probably do it in India also because it looks so beautiful. You have this line, and then somebody who wants to cheer his crowd goes, "Whoa!" He cheers his team. So he goes like that, and then the person next to him, as soon as he sits down, goes, "Whoa!" and sits. And then the person next to him goes, "Whoa!" and sits down, and this thing goes on. And it's like a wave of woes. So, well, here we don't have too long. But here, let's demonstrate it on the second row. You don't need to stand up. Just raise your hand. Start here. Okay, so, yeah, that already continued. That's wonderful. But it goes by a row. And there is nothing more linear than that. You saw it. It goes up and down, up and down. So the wave is the most linear thing in the world. It's beautiful. So if it's the most linear thing in the world, so let's do the wave. All right. What does it mean? It means the following. When we say we want to know every element in the text, what is good for it and what's bad for it, how do we know what's good or what's bad for the element in the text? But we can, of course, use the wave in order to know it, because here is the idea. Suppose that these guys in the circle, they're the potential candidates. Now, we want to know for the text in every position, what's the pattern element that text wants to see. And the way that we do it is by a wave. Because if I tell you that the pattern is of length 6, and the pattern starts here in this circle, then he starts a wave and he says, 1, I want to see a 1 in this position. And then the second element that you can't see is hiding between the two of them. He says 2, because if he wants to see P1 here, so I want to see P1, then the second element wants to see P2. And then he sits down and he says to the third, go on. And he says, okay, P3, because if this is where the pattern starts, this should be equal to P1. This should be equal to P2. For it to be good, for the text to be good, this should be equal to P3. And he says to him, continue. So he says P4. And then he nudges this guy and says, come on, say P5, because you're next. He says, P5, your mother. I am starting a new wave. So I'm going to do P1. So he yells P1 because I'm starting. So I'm going to do P1. And then he says to this guy, do P2. So he wrote the 2. And then he says to him, write 3, write 4. He says to him, write 5, and he gives him the finger. He says, no, I want to start a new wave. So he starts 1, 2, 3, 4, 5, 6. So at this point, the wave dies. Now, in fact, this also, it works when I do the wave in a big class in Israel, because I tell a row to do a wave, and they start a wave, and then they get to someone who is very dry and sense of humor challenged or something, and he doesn't want to participate, and at that point the wave dies. So here also the wave dies. 1, 2, 3, 4, 5, 6. The wave is dead because the wave is of length 6, and there is no more candidates. Now, so our claim is that at this point, if I want to say what of the text is good and what of the text is bad, all I need to do is compare the text to P of the index that is written here. And if what's written in the text and what's written in P of that index is equal, it's good. And if it's not equal, it's bad. Now, the question is only, but wait a minute. These guys, these rude guys who did not participate in the wave but started a new one, don't they ruin something? I mean, how does this guy know that this is good for him? Because we started a new one. So he wants to see P1, but he wants to see P5. How does he know that there's a match for him? This is why we did the duels. They're both candidates. It means they agree on the overlap. So the fact that he wrote P1 doesn't matter because P5 is equal to P1. And I know that it's equal because if they weren't, they wouldn't both be alive. One of them would have died in the dueling stage. We proved the dueling stage. It kills everybody who is not, who's in conflict. Everyone who is left, they all agree. We very painfully proved it. So this is equal to P5, and this is equal to P6. So if this is equal to P1 and this is equal to P2, he's happy because what he wants to see is what he gets. But he's also happy because what he wants is what he wants. They really don't disagree. And so in linear time, we do this wave. There's nothing more linear than that. We do the wave, we put the indices, and we run through and compare the text to the index. And now every text position is either good or bad. So we end up with something like this. We end up with something like this. Now, I'll move it up a bit, even though so we end up with something like this, meaning we have a text with some elements good and some elements bad. So the yes are good. The yes means that the element is good in the text. The no means that the element is not good in the text. Now, the point is that once I know what's good and what's bad in the text, the good are good for everybody, and the bad are bad for everybody. So this n is bad for him. So obviously, this guy, even though he survived the duels, there is no pattern match here because this n is going to say, well, what you want to see here is no good. But it means that it's no good for this guy also because the pattern is of length 6. So this guy also doesn't work. On the other hand, this guy, in his entire horizon of 6, there are no n's. So what he wants to see is all there. So we know who is good and who is bad according to who has an n in his horizon. But now we're presented with the symmetric problem. How do we know, in an easy way, without too many formulae, who has an n in his horizon? And the answer is we do a wave, but we do it backwards. So now we start a wave from every n. So every n starts a wave, but it goes backwards. And it counts 6. So this n starts the wave, 1, 2. And he says, you do 3. But he says, no, I start the wave. So he goes 1, 2, 3, 4, 5, 6. And then the wave dies. Any potential candidate that finds itself in the wake of this tsunami drowns. So now we come, so far today we had cinema, we had literature, we had comedy, but now we're going to get to a little bit of medieval history. Now, the Europeans, especially in the Middle Ages, were a bloodthirsty bunch. Some would say they haven't changed, but okay. The point is, in the Middle Ages, they used to have all kinds of easy ways of meting out justice. So, for example, if someone was accused of being a bad person, so they would have the fire test. They would burn him, and if he burns, it means he's a bad person. And if he doesn't, then he's a good person, so he was right. Or they would have the water test, so you throw him in the river. If he drowns, it obviously means he's guilty. And if he doesn't drown, then it means... So they used to call it the fire test, the water test. In this particular algorithm, we actually had both. Because you can look at the dueling stage as the fire test. There's firing, and there's shooting and shooting, bam, bam, bam. And when the smoke all clears, you have a bunch of people still standing there. Whoa, I survived the firing stage. These are the potential candidates. And then, little do they know that here they are still standing there, these guys, these circle guys. They think, I'm out of it, and then all of a sudden, whoom, this tsunami starts here, and there's this big wave, and it starts, and it washes this guy, and it washes that guy. And he's standing there looking with fright at the tsunami coming towards him, and he died there. So anybody who withstands the fire test and the water test, these are the people who have potential, who actually have a pattern occurring in them. And that's the end of the algorithm. We proved everything in this case, except for, what didn't we prove? Yeah. I will say what we haven't proved, but let me also say something else that's good about it. There is no binary search in this entire algorithm. As you can see, in every stage of the algorithm, there was a comparison to something, and it's either a yes or a no. There is no search that's needed. So unlike the Aho-Corasick algorithm, for example, where you needed to search what back arrow do I go to in order to know which of the paths in my automaton I need to go to, and that's what gave Aho-Corasick the logarithmic slowdown in infinite alphabets, because how do I know what letter to go to? I have to search for that letter. I have to search for that letter, and I do it in a binary fashion, which gives the log. Here, there is no logarithmic search. Everything is straightforward, which is why, when we're going to see tomorrow the two-dimensional version, we're going to see that, again, it's going to work for a infinite alphabet as well. And so the world waited from 1976, when the first algorithm of Bird and Baker for two-dimensional matching was published, and it was alphabet dependent until 1991, when this algorithm was published, and it was shown that it's independent in 2 dimensions. But one thing we haven't shown, that's the 2-dimension, forget the 2-dimension. So the one thing we have not shown is the following. Witness table. The whole thing works. I said we have the witness table, and that tells us how to do the duel. We forgot right now already that duel thing, because it was somewhere inside the machinery, and we even forgot it. But we needed the witness table for the duel. We need to construct the witness table. And we need to construct the witness table in linear time. So the question is, how do we construct the witness table in linear time? And this is going to be what you're going to think about tonight. So tomorrow, we may talk about how to construct the witness table in linear time, but we'll start with that, which I encourage you to do, but let me give you a little hint of how to go about it. So again, you're going from left to right. And assume that you have constructed your witness table up until here. And the question is, what can you say? So you know everything in the witness table up until here. And the question is, what can you say about the next guy? Because up until here, we constructed the witness table. Now, what does it mean, the next guy? It means that I'm putting here the pattern, and I want to find out in the overlap where are we bad. Okay, so suppose that already these two are not the same, then you can fill this one in the witness table and go on, and the time is O of 1. Not a problem. When is the problem? When you actually compare these things and everything is equal, and you keep going and everything is good, and only here finally I find my witness. So the beginning and this, I compare them one to the other, and my witness is only there. So obviously I can write my index. I can write my index of the witness in the witness table, and that's good. But then what happens to the next guy? Is going to also have to check everything, and the next guy is going to have to check everything. So how do we handle that? So here is the key when you try to prove something like this. So what you say to yourself is the following. Okay, the fact that I went on all the way up to here, I went on very far, and the only witness was very far away, it means that all of these guys are equal. But what does it mean? It means, who are these people? It means that all of these are actually equal to all of these. And we already computed the witnesses for those guys. So the idea is, how do we use the witnesses that we've computed for when they repeat? And so that's what you need to think. There are a couple of cases to work out. And then you can fill out the table in a linear time just by using the witness tables that you already computed in the past. So that's the hint. Now, that is not to say that it's finished. There's a lot of things to work out, but I think at this point, you have all the tools to work it out if you so choose. So we'll see you tomorrow.